Right. Good morning.
Good morning.
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 Maybe I'm not loud enough. Am I not loud enough?
Yeah.
Good. All right. Beautiful Heritage Day. Welcome to Johannesburg. Welcome to South Africa. Most of you probably the first time in South Africa. So we're happy to have you. My name is Livo Makondo. I'm the general chair for this beautiful event that we've managed to put together in 8 weeks. By profession, I'm also a research manager at ICRA Research Africa, in Johannesburg, and also a visiting researcher at the School of Computer Science. Previously, I worked at the CSR as a robotics researcher at the Mobile Intelligent Autonomous Systems Lab. Rebranded now, but they're still the All right. The reason we're here is to celebrate ICRA. This is IEEE's Robotics and Automation Society's premier robotics conference. The main celebration is happening in Rotterdam, Netherlands. We are satellite event to that main celebration. So they started yesterday. We kicked off today. So we have our own branding of. That's a much cooler branding that. They should smell us
Soon.
So this is all made possible by the IEEE robotics and automation. So they came up with this idea of having such events, and they thought, why not Africa? So they approached us and say, you guys organize. Because of the short amount of time we had, our approach was to invite a few key people that are doing robotics across Africa to come with their students. We were overwhelmed by the amount of response that we received. So we are grateful for you guys. So the IEEE Robotics and Automation Society is part of the larger IEEE organization. You can see the numbers that is a huge worldwide organization. So the RAS society focuses more on robotics and deployment of robotics and automation. They do host several conferences with ICRA, recently here, being the largest conference that they have. And they look at different areas of robotics, from software, hardware design, and they do look at different sectors. I know some of us are working in these areas. Now, like I mentioned already, so we are the satellite event to the main event in Rotterdam. And we're really here to celebrate robotics research in Africa. So they're celebrating robotics research worldwide. We thought we also want to celebrate robotics research. We're also looking at creating network opportunities. I think there's a lot of good work going on in silos, and it's really good work. But I think to have impact continentally and also globally, we need to pull in the resources and expertise together and collaborate. Also, to pull in the resources. The vision is trying to build this robotics and automation society in Africa. and I'll talk a little bit about that. We're all doing this in African style on Heritage Day. So just talking a little bit about community. So we really have limited resources looking at talent, funding, infrastructure. And if you want to make impact locally, you really find ways to pull this together. There are many different ways we can look at that. We can work on joint supervision, sharing job opportunities, applications, and looking at building startups in the African continent. I think there are a lot of startups being developed elsewhere. There has been some momentum recently to have startups here locally, but I think there's a lot more that we can do by coming together and pulling those different resources. We also need to work on building international collaborations, networks. I know some of you individually have this, but I think we also need to leverage those to strengthen and expand them here in South Africa and also to the rest of the African continent. Also looking at joint funding. Funding is a big problem. I think there are big opportunities for funding globally. I think this conference is one such example where we have international organizations sponsor events on the African continent. We don't have to start from scratch. So there are a lot of communities being built in the AI space on the African continent. On the right, so we just highlighted some of the communities that are looking at research and development of AI sectors. I'll just highlight maybe Latin AI that's looking at increasing the representation of African researchers on international conferences, starting with Europe's and also expanding to France. We have the deep learning in Ndaba that really has expanded from its roots here in South Africa at University to the continent. In fact, we just returned from the conference in Senegal. It's been really busy. Also, I think we're also lucky to have one of its co-founders, Benjamin Rossmond, sitting with us. There are many other organizations like Masakane looking to pull in expertise and resources to create data sets for training machine learning for African languages. Also have AfriClimate AI looking at data sets for applying AI for satellite and spatial modeling. And most of these are really attached to that's where the getting. Now, on the robotics side, there has been some activity. Some of us here organized the Local in Africa workshop. In Ghana, the second workshop. The first one was last year in Ghana, now in Senegal. There's also a Robotics in Africa forum at IROS this year, another IEEE organization. In fact, when I was looking at I saw that Paul is invited as a speaker there, as well as myself. So, good to do that. But also locally, we've had some organizations looking to create this robotics research environment, mostly in South Africa. We have RobMech, which is the Robotics and Mechatronics Association of South Africa, that is collaborating with the Pattern Recognition Association of South Africa. So that has really been more locally focused in South Africa. But when we're looking to build these communities, have impact on the African. So there's a lot of work, a lot of examples. Now, looking at the participation at this conference, so try to get more participation from all over Africa, but of course that's impossible to do in 2 weeks. given all the visa requirements. So we couldn't get our Nigerian delegates to get their visas in time. We were able to get Kenya. Most of our delegates are coming from South African universities. University, that's UCT, University of Johannesburg. So we appreciate you guys making time. There's going to be a lot of work. There's going to be a lot of talks, interesting talks. It's going to be a very busy 3 days, but we're also going to have fun. So the team has put together, some activities. Tonight we're going to visit the Sedi Cultural Village, just outside Joburg South, where we look at, the culture in Africa, mostly South African, and how modern culture has evolved. There's also interesting food. We will have challenge. Funny words. Then on the last day, we also organized an event at the Festival Center where we really go back to look at the origin of humankind. So I'm really hoping to show our counterparts in Netherlands that we actually have much more fun here. Lastly, I just wanted to highlight the organizing committee that has put together this conference. It has been really, really trying, but I think we managed to pull off a really good conference. I just wanted us to give them a round of applause. So please interact with them. Thank you. Right. Next, we have organized a panel with two colleagues from Google Research in Kenya. So this is Aisha Walcott and Sekou Remy. They are former research scientists. The reason why we invited them here is because most of us have robotics background, but have been leveraging expertise.
I'll make up an agenda. Thank you. Hi, Ndivo and everyone. Thank you all for joining this event today. Hope you can hear us clearly.
We can hear you, but we can't see you yet. Just waiting. That's on our side.
Okay, no problem at all. I'll just give a context of a couple of points that we will discuss, and then most importantly, we want to hear and have conversation with the participants, all the members there, questions, even ideas for the future for robotics in Africa. How are we doing? Almost there.
Almost there.
Yeah,
Getting closer.
it's like infinity. Yeah, so as you get this ready, so what Sekou and I'm Aisha, will do is we'll provide a little bit more context on ourselves and our background, especially as roboticists by training, and then talk about how that background has helped with the work that we've been doing in Africa. And we'll hone in on one example where, kind of one of our core, there we go, core favorite algorithms that is now very popular, reinforcement learning, has been translated into work for impact on the continent, but how robotics helped to seed that process. So let me start then with Sekou doing an intro of himself, background, and then I'll do the same.
All right, so hi, good morning. My name is Sekou. I'm a research scientist based in Nairobi. My background is electrical engineering from Georgia Tech, where I was, as a grad student, really interested in the space of how robots learn from examples. And in essence, the concept of a robot learning to give feedback about when it was done learning, that was the nugget that I was really interested in. I did a little bit of a pivot in terms of one of the problems that I had, and every roboticist I know will understand this problem, is to do the experiments, your hardware has to work. And some of the core contribution that I was interested in as a grad student is that instruction, that interaction between the human and their robots. So there was a question that I was exploring about, okay, well, what can we do that is meaningful in the space of cloud robotics, where we can get robots at scale, and we can get the robots wherever they're needed. So there was a bit of an interesting detour that I took that allowed me to gain a lot of deep exposure into cloud stacks and how we can consider cloud as a cyber-physical system itself, because these are distributed systems, just like our networks of our swarm robots, and the impact of latency, the impact of processing speed. All of these are things that change what closed loop, what feedback control look like. So it was an interesting opportunity to pivot. And as Aisha mentioned, and we'll get into this a little more, when I made a switch into healthcare, one of the questions that people initially were asking is, okay, you went from robotics to healthcare, how does that work? At the core, I view myself as a problem solver, but it was really cool when I was finally able to bring robotics into the chat. But yeah, so happy to be here, happy to have this brief moment to chat and, in essence, think about how things have been.
So then after this, we will then say, how did we get here from where we were? Okay. So again, I'm Aisha Walcott. I'm also a researcher based in Nairobi, Kenya. I've been working here for over a decade, and my robotics background, for me personally, robotics just felt like my nature. Even as a child, I didn't have a term for it, but I loved the digital physical interaction. So I loved working with circuits and seeing things move. I went to Clark Atlanta University for my undergrad in computer science, and then I went to MIT for my master's and my PhD in, I don't know. Okay. And master's and my PhD in robotics at the Computer Science and Artificial Intelligence Labs. So similarly to Sekou, sort of thinking about the problem, I started off, well, my master's was on heterogeneous multi-robot teams doing path planning and task planning, so unifying those two together and getting them to cooperate to work on a task. A lot of our stuff, we made a Martian test bed, which many folks do now, and had a few robots that we could also build from like laser cutters, and so sort of local mechanic kind of stuff, because really you just needed the SBC, the single board computer that would handle the controls of the system and the real-time operation, and then sort of pipe your high-level algorithms over the internet. Now you can see how old I am. I know you guys have all of it on one chip and it's working great. So yeah, I worked on these multi-robot teams, but then what was interesting as I was working on it, more from a planning perspective, as I was working on it, what I realized is the group I was in, we would plan tasks, like let's say robots need to do this science experiment, and then these tasks would be hierarchical. So it would break down and say, okay, these are the activities, here's the estimated time, here are the constraints to do this task. And then underneath it, there was no path planning. And so what that helped me to think about is like, as much as I was thinking about planning and achieving a task, we weren't really achieving it from a fully autonomous system perspective. And so what I did after working on that for my master's is I ended up working more, let's say, closer to the robot. And that was on simultaneous localization and mapping, on SLAM, which I'm sure many of you all are familiar with. And so I worked on SLAM in dynamic environments using the laser, using laser for the main sensor for the world, or to recognize the world. And that I can see how these pieces could couple together and then eventually create the task. But there was always some complications underneath of it. So this is kind of my problem-seeking journey as a student. And then I've transitioned, like Sekou has, into many domains as I moved to Africa and wanted to have impact on Africa. So maybe now we can talk a little bit about how we've gotten here and what we've been working on here, and we'll deep dive on one.
Okay, so one of the pieces I would actually say is we are problem-focused people looking for, in essence, trying to understand what the problems really are. So I'll never forget having a conversation with one of my mentors, like, okay, hey, I'd like to do robotics. Where is there robotics in Africa? Jokingly, and I'm sure many of you in the room have already heard this joke, well, in South Africa, traffic lights are called robots. Not the same thing. But it was interesting because when we talked then, this was, let's say 2015, the potential or the opportunity for robotics definitely was there, but it's not much different from the potential or the opportunity of cloud computing, because that was the other thing. Because again, I had a background in robotics and then I grew into a background in cloud. But one of the questions that people kept asking was, okay, where can you apply these skills that you've learned, all of that nice fancy math, all of that experience or expertise in these domains? And then I had a conversation with Aisha, in essence, about, hey, at that point in time, we were doing work in health systems where people were saying, okay, well, we have distributed hospitals or people receiving care at multiple different facilities. And one of the questions that was being asked is, how do you share information between facilities or between places where people do receive care in a manner that is sustainable, where there's an opportunity for trust? And it ended up being a very, very, very practical, tangible cyber-physical system where we needed to ask a question. How long would it take for this piece of information, these bytes, to get from this location to another? Not very different from an IoT or a robotics use case, especially since we were talking about closed loop systems where you actually needed to get a response or an acknowledgement for a piece of a message. But that insight only came because as a team, there actually happened to be a lot of robotics presence. So we had a lot of EEs for whatever reason, a lot of computer science for whatever reason, people who understood the concept of a feedback control loop, working on this healthcare project. And there were elements of saying, okay, well, we understand the physical problem, we understand the relationship between time, space, and we also understand the solution that's needed. Because at the end of the day, for us, we were working with doctors and medical officers and nurses, and their primary concern is the patient. And then their secondary concern was the patient and the patient. And then maybe the other concerns is, okay, how do we make sure that we're not in this hospital for the entire day? If you have a queue and there's some technology that you want to deploy or try, that technology better not make problems worse, because we're talking about people's lives. So it was an interesting opportunity to first ask this question: how can we help? What's the problems that you have? And in our case, we weren't looking for the opportunity to say, hey, here's how our robotics background can help.
Right.
But it was really cool when we were able to see that first one. You want to talk about the second one?
Sure, yeah. So first, I'd like to acknowledge this moment. After more than a decade in Africa, I have not been able to talk about robotics because we haven't had the immediate practical, let's say, applications. And then I say robotics in a robotics setting with a bunch of other practitioners in this space. So kind of amazing on where we've progressed to. and the opportunities ahead of us. The other problem that, again, worked on with Sekou and others at the helm who understood, still, let's say, the robotics background, the algorithms background that you get when you study robotics, was around malaria control. So thinking of what are the interventions, or in our case, what are the inputs that you can put to the system, which we would call a robot, but this system can also be any type of model, and not necessarily an AI model for that one. It's a model, meaning a representation of the world or some effect in the world. And then what are the potential outputs? So if you start with thinking about the model as a disease model, in this case, a malaria intervention model, then you can put in a set of inputs to say, if we do these activities or actions, then the world will look like this in terms of, let's say, prevalence of the disease or outcomes of the disease. And this can be done in many ways. We tested it really mainly from a population perspective. So what proportion of the population might get malaria, and obviously you want to reduce that number based on these inputs or these actions. So this is a well-framed reinforcement learning problem, if you think about it at the core, where as you make a set of decisions, you want to know what is the impact on the world and understand what is the reward to know, where to go next, what to do next to get closer to your goal. And in this case, your goal can be whatever healthcare target or population health target that you want to achieve for a community, a region, and that can be prevalence of the disease. Maybe it's currently at 26%, but we want to get it down to 15%. So you need to think about what are the actions to take in order to achieve that goal. And I was absolutely thrilled to work with Sekou and others who, were quick to be able to translate this locally relevant healthcare problem into a reinforcement learning problem, which sort of for us brought it home.
One of the things I'd say about that is when we started, yes, malaria was the domain, but that came actually kind of naturally because this particular project started as an intern project. And the student involved was really curious, like, okay, well, I know that we have all these optimization controls things, but none of these things connect with me. None of these things are directly impacted to lives and livelihoods. At the same time, I had just joined my previous company not that long ago. And one of the last projects that I was wrapping up was evolving controllers for bipedal robots. And I was like, okay, well, maybe there's an opportunity to actually have something that looks really similar. And the more that I looked at the malaria domain, it was, hey, this is just a second order differential equation. So the system dynamics for disease progression in malaria was very similar to inverted pendulum. And it's like, okay, well, maybe there's a there. So we spent a bit of time just exploring the literally, how do you make something like this work? Let me not say everything. OpenAI Gym existed at that point in time, but most of the environments that existed in OpenAI Gym were, again, your standard classical control environments. And now we were asking the question, what could we do to allow, quote, a malaria environment to be injected? But our point was never malaria. Our point was, here's a practical application of RL techniques in a domain that is not RL. It's a new type of environment, and it's an environment that we thought would have been challenging, would have been interesting, and allow people to connect. Unfortunately for the world, the pandemic showed up. But for us, it was an opportunity to say, hey, this is what we've been telling you all along. COVID-19 is a disease. It happens to have dynamics equations that are similar to those that were implemented for malaria. And hey, the same solutions that we've been telling you about, the same algorithms that we've been telling you about are relevant in this space as well. So it was a cool opportunity to say, and this is what we've been telling you. What was also interesting is that all of the same agent-based simulation environments that we are currently, we commonly see in robotics, they exist in the epidemiological space as well. And they are struggling as a community because they don't have the same type of experience, they don't have the same type of history with encountering, whether we talk about control or calibration strategies. So they're doing things that they were able to directly see, oh, this is how robotics can help. But there was a piece where there was a bridge that needed to be built. And to build that bridge, you needed to both understand what they were doing and what we could offer, and then figure out how to actually have a conversation. Because without that conversation, it's just, oh, you robotics people might think you're going to solve all our problems, but you don't understand what we mean. Or there might be an assumption. So for example, roboticists love the ability to linearize a solution. Okay, well, what are the implications of linearization in this particular problem domain for health? What could go wrong? And what are the implications for the types of solutions that you can explore? Or how does uncertainty quantification matter? Or what are the ways that all of these nice experiences that you have, whether they're textbook or real world, translate into this different domain? So it was a really interesting journey. But yeah.
Yeah, I think we can pause there and open up for any questions.
All right, Devo, we can see you.
Yeah, and ourselves. This is fun.
But we can't hear you yet.
We cannot hear you.
No, we still can't hear you yet. All right, so while that gets sorted out, one of the other things that I found was interesting is offline RL made a significant, no, we still can't hear you.
Oh, they can hear you.
How about now?
Yes.
Great.
All right.
Any questions or thoughts? Yeah.
You should have mics all around so we can give it a try.
Okay. Hi, I'm Dr. Michelle Johnson. I'm from the University of Pennsylvania. I was really curious about the work that you were talking about with the hospitals in terms of trying to apply that as a cyber physical system. Can you just talk a little bit more about like what were the outcomes of that and kind of like what were you like transferring data or assuming that each satellite hospital was actually a physical system? Just to explain a little bit about that. I was really interested.
Yeah, so this was a research project that our team was, we got bitten by the pandemic in all of the bad ways. You don't want to deploy an experiment, especially that involves going to a hospital in the middle of a pandemic. But we actually did. So as we were preparing for that project, one of the questions that we had to explore was if we were deploying infrastructure at hospitals. So basically we did a pilot and we said, okay, there are 2 different hospitals and we're trying to test information sharing from one site to another. And the hospital itself had to be the location where the simulated patient data was housed. So you went from one physical hospital to another physical hospital. And if you wanted to share information between, let's say, 2 encounters that are happening at different hospitals, the infrastructure needed to support that. So I don't know if you've had this experience, but there is a fair amount of latency. Africa is a massive continent. Yeah. But even if you don't leave Africa, sometimes within a country, you can have a significant amount of latency because let's say that message is going to another country before it gets back to the other part, right? So there are times where a message may leave South Africa, go to, I don't know, France, and then come back to South Africa because that's just what the infrastructure looks like. So we actually needed to study that network topology. What does latency look like? What does jitter look like? Because these were things that impact the overall performance of the system.
Yeah, and just to to provide a little color of like the scenario that we were looking at continuity of care from the community, which is very common in Africa, where you have community health workers, and to lower to higher level hospitals or health clinics for care, and having that at-home patient visit data be a part of a privileged and shared, let's say, network, a permissioned and shared network across these different health facilities and the home. So we didn't want, our aim was to be able to unify this care, especially for long-term chronic conditions that where most of the care happens at the so that was the context. And to Seku's point, well, actually, the first thing he said is like, no one wants your experiment if it really messes up with their workflow, right? And so this talking about latency and how to represent this problem as a distributed cyber physical system, we started off with doing this in a very rural, they call it like level 1 healthcare facility and community setting. And they were very agreeable. They understood research. They were from, I think it's, which was the university?
Vanderbilt.
Yeah, Vanderbilt University. And so having that understanding of research was very important in order to even test this concept. And then we tested it, we scaled it up, and it generally showed one level of feasibility to go into a setting that we weren't so familiar with at all with another partner. So there was a big shift, at least for me, from robotics to healthcare, which was humans. So I did have to, and I'm still warming up to humans, but that broad potential of impact is just so infectious. And we talked about diseases in a positive way, that I love the fact that my robotics background and then my sort of new foray in healthcare came together to work on a practical problem that impacts lives. Long answer to your wonderful question.
Thank you. Those are all
The audience, I know some people.
Well, we are running a bit out of time. If you want to stick to schedule, I think we'll have to thank you. And looking forward to interacting with you guys in other capacities. Thank you.
Thank you.
All right, thank you for inviting us. Bye-bye.
Bye.
All right, next, I'd like to call upon Paul Amayo. I was going to lead the next session. Sure.
Yeah, thank you all for joining. I was gonna say thanks to Aisha and Seku, but they've already left. It's a small but wonderful community. Aisha was actually my boss when I was an intern at IBM, and I met Seku quite recently. So it's all of these things, all of these networks that we're doing together, they bear fruition in time. So yes, we're really good. So just firstly, a little bit of logistics. So the coffee will be taken outside to your right, and then there are bathrooms just down the hallway there. Going into this next session, we want to talk about you guys and all of the labs and all of the things that you guys have been doing. We're going to showcase a little bit of a video montage showing the cool stuff that's happening within South Africa within robotics. And then we'll have a little bit of a presentation of history from Prof. Cornelius from Brown University, who talk us through, some of the robotic history in South Africa and things that he's looking forward to in the future as well. So yeah. Infinity mirror.
Infinity ball effect when you were talking. Not the ones I sent you.
Sorry, while we work through the technical challenges, I realized I came in and I said things, but I didn't introduce myself properly. I'm Paul Amayo, Dr. Paul Amayo. I'm an academic at the University of Cape Town. I'm a member of the African Robotics Unit. Previously, I was in Oxford, where I did my PhD in kind of autonomous vehicles. I also am a visiting faculty research at Google Research Africa, so that's how I know Aisha and Sekou. There are a bunch of students.
Hamburg for Eurohaptics 2022, and we hugged more than 100 people over the course of several days. This is the third speaker in the session today, and we are really honored to win the prize for best demo. So the last project I want to tell you about is much more recent.
We've been hijacked by the main country.
I want to tell you about is the doctoral dissertation of my PhD student, Natalia Sanchez Tamayo. And we are working on how can we give good haptic sensations on hairy skin. So your hairy skin covers most of your body, and it's much less sensitive than the skin on your fingertips. So we all have devices like this, and what do? They buzz. That can get our attention, but it gets a little annoying, and it's not appropriate for all kinds of communication. And so we wanted to create a device that's just as compact and usable, but that can also make and break contact with your skin.
Early coffee break. We will come back and do the
Previously, when he was at University of Colorado Boulder, had co-invented these hazels, these artificial muscles that I think are like miracle actuators. They work so well. Each one, we make little pouches that are filled with oil. They're like a bag of oil with electrodes on the outside. And then you apply a voltage. It might need to be a few thousand volts. Then it squeezes together and you get extension. It's very low current. They're basically capacitors. And we put a stack of 10 pouches. We assemble them together with an elastomeric layer, and we mount it off the skin. And then when we apply the voltage, we can make and break contact with their skin and deliver broad bandwidth vibration transients. This is how it works. When you're looking from the side, you can see when we increase the voltage, we can press on the skin, we can do it gradually. We can play wide vibrations. I'll just watch one more video. You can see we can vibrate really.
I'm doing my post.
Take us in a butt if you would. Let's get in a bus for an hour and a half. Yeah. Then we're gonna have the whole thing. At night, we're gonna come home for an hour and a half. Drop us in breakfast.
Speaking of park, you wouldn't believe where I got the thing is, I didn't check the venue, right? So I just said it'll be somewhere on East Campus.
All the way.
And then I put Google Maps.
sitting here streaming.
I'm gonna get my car with my laptop and things there. So it was very
Hang on a second.
you keep in this road and I think it's the longest distance I've traveled through.
I didn't even know I was supposed to be holding the right button. I jacked it straight down. You said he's the AV guy. So the main contact. I want to try a video. More about that.
Very flattered and excited about participating. Especially, very short. It's funny that though you just
Very good.
There. And when I got back, and I saw, I know, I was like, oh, no, I'm super excited about this. No, it was funny. Because part of it was about like in the Netherlands. So I brought up, I said, hey, I'm going to be a keynote at ICRA at 40. ICRA at 40 in Africa.
Everyone's like pulling out their phone.
I know, and then they ended up, I was like, oh, there's a satellite event. And I was like, yeah, I think this is important because I've been talking about getting robotics in Africa. So, this is exciting. So I was like, I gotta go.
Right, and it's awesome that yeah, this was like the first experiment before you.
And I look forward to doing it.
That's amazing. Grab some coffee.
No, I'm
bit later.
yeah,
There's people with the biscuit notice you.
I thought I'd be good before. Yeah, I made that one. It's kind of cool. That's
Just edit that.
Yeah,
You mastered.
Yeah, mastered.
And added like the transparency.
Exactly. But it kind of looks cool. Like
It looks like it's. I'll be playing that again in my talks. Good man.
I thought here first didn't realize that when you presented that the whole and then
I'm gonna get coffee.
I said it was just this session was the problem child.
Yeah, we had to do it first.
Well, I want to put the video on the
desktop. I'll put the video in now and then click like a share screen.
the videos on this computer.
Yeah, just change it there.
Yeah.
So the video
Play
here.
the video.
The video is currently playing. It just doesn't have
Anyway, I'm here today to talk a bit about some of the work we've been doing in our lab. So as was mentioned, I direct the RAIL lab, which is based here at WITS. That's a Robotics, Autonomous Intelligence and Learning lab. Many of the people from our lab are here today. Well, actually, it's just a small percentage. And I hope you get to know all of them. And hopefully we can organize that you can come and visit the lab as well while you're around. And I want to talk about one of the kind of streams of work that we've been working on. So we do a lot of work in robotics, we focus a lot on reinforcement learning, and we kind of sit at the intersection of these two fields. And so I'm going to talk a little bit about some of the kinds of projects that we've been working on. Now, obviously, what we care about are these guys over here, robots, which we want to get to be more capable, be able to do kind of a wide variety of different tasks. And this is really the kind of question that drives our work, but really doing this in the context of people, right? It's important to remember that we don't live in a world completely populated by robots, maybe not quite yet. So we have to deal with these annoying, like, flesh bag things that wander around. And, try and do things in a positive way. And to me, the kinds of factors that we care about are building robots that are firstly flexible. We want them to be able to do a lot of different things. We want them to be instructable, right? And this comes down to, at the core, working with humans. Right? So if I've got my robot here and I can't tell it what I want it to do, what's the point, really? And finally, it should be reliable, which means if I tell it to do something, I would like it to actually do the thing I told it to do. Now, the way I think about this is these first 2 points over here talk to a system being general, right? If it can do a lot of stuff, if I can easily instruct it to do different things, right, then that's a general system. Then if it's instructable and reliable, that's what I would think of as being safe. So I think these are kind of the two driving principles that we think about in a lot of the work we do in our lab. So how do we kind of make this happen? Well, first let's look at kind of an example of a problem that we might care about. And shout out to Brandon for all the awesome animation work. But let's imagine the setting in this simulated office world where you've got a robot over here, and there might be a whole lot of different things I care about. So maybe I wanted to go and fetch mail because this is old school from the mailroom, and then we should take that mail to the people who need it in the office over there. And maybe the other people are sad, so we should take them all coffee. And then we're done with tasks for now. So let's just patrol around some of these locations, 1, 2, 3, and 4. And the whole time we're doing all of this, let's just not break or bump into any of these decorations. Right, so that might be a perfectly reasonable and fairly elaborate task that I could want my robot to do. And you can imagine a whole infinity of these tasks that I might want my robots to do. And this is like that flexibility, right? So we've got this flexibility of these different kinds of things. I'd like to have some way of specifying to this robot what I want it to do. And I'd like it to actually do the things. Ideally, not breaking the decorations and so on. So this might be a kind of like higher level problem that I care about that we want to tackle. The problem is this is quite difficult to solve. So how do we think about this? Well, at the core of what we do, we think about behavior learning, right? And this is the idea that, like, if we want this kind of flexibility, we can't pre-program our robots. We can't design like controllers for each individual task. We really want them to be able to learn to solve problems. If we're thinking about learning, we kind of fall naturally into the reinforcement learning paradigm. Or for those who are not familiar with it, it's like sitting at the intersection of, well, it's basically stochastic optimal control where you don't know your models and you don't know your vector function. The way we think about this is we've got to learn from trial and error. We have our robot and it exists in some environment. Everything's about that interaction between our agent and our environment. So our agent takes actions there, right? And this could be moving, this could be opening doors, whatever that might be. And then the state of the environment changes as a result. And occasionally we get some sort of feedback signal, the reward, which is what we're trying to optimize. Now, this is the very basic setup of all of the problems that we all kind of work on. But there's some challenges over here, right? And particularly we must remember that the actions and states are typically low level when we're thinking about robots, right? We've got joint angles, we've got pixels in a camera, right? So we've got all this kind of high dimensional nonsense we're going to make sense of to solve these complicated tasks. Okay, and then finally we're going to think about, like, where does this reward come from, right? This arbitrary task specification that I'm talking about. Okay, so maybe just a 2-minute summary of reinforcement learning before I go into the actual interesting things. So the reinforcement learning setup, we often think about it as what's called an MDP, or a Markov decision process, which is a 4-tuple. So we think of first the states, which are all the different configurations of the world that we might care about. So this could be the position of the robot, this could be if the door is open or closed, and so on. We've got actions in this very simple toy case here. Might be move left and right, open the door, grasp an object, and so on. So a set of all of the things that our agent can do. Then we've got a transition function, right? And this describes what happens. If I'm in a state, I take an action, what happens? Like there's some distribution over like how the world evolves as a result of that. And then finally, there's some rewards, or like the objectives, which is like maybe I get +10, I'm very happy for getting a present, and very sad for falling in a hole. Okay, so these kind of 4 elements we can use to model the problems we care about. Now, we can't model everything, we can discuss exactly if this makes sense, but this is a good starting point for these kinds of problems. Then, of course, we've got to remember that typically the states are kind of very low level, high dimensional, and the same with the actions as well. You're typically in robot land, you know, actuating joints and that sort of thing. So if this is the standard reinforcement learning problem, we then want to obviously solve these kinds of problems. And again, the one thing to point out is this reward function that's encoding what we care about is task specific. So if I want my robots to go and pick up, like get a coffee or pick up mail, this reward function is going to change for each one of these things, right, which makes our lives more complicated. So if we have this problem set up, what we care about is the policies, right? So the strategy that we're solving here, and what we really want is an optimal policy. And this is like the sequence of actions we should take, or more technically, it's like a distribution over actions for each thing. So if we're acting optimally, what we might want to do is move to the right, open the door, and pick up the object here. That's going to maximize our reward. So in learning an optimal policy, we kind of, like in the reinforcement learning setting, we don't have the models. We don't have the dynamics. We don't have the reward functions. And so we typically learn through trial and error. Like a robot bumbles around the environment, tries things, makes mistakes, gets some feedback, and learns from that. And that's really slow, which is the first challenge we've got to deal with. Then it's difficult to define the feedback that our robot's getting, right? That reward function I was talking about. If I've got some super elaborate task of moving around this office building, doing all these things, how do you define that? By putting random positive and negative numbers all over the place. That's a really hard thing to do. And finally, to do this over really long time horizons is difficult as well, right? I've got this long sequence of tasks that I want to, or subtasks that I want to execute. That's challenging as well. So these are kind of the 3 big problems I'm going to focus on and talk a little bit about how we're thinking about this in our work. And one quick thing is, just before we go into it, often a solution we might take to solve these problems is to learn something called a value function. And a value function is basically like for you want to know if you're in a particular state and you take a particular action, how good is this going to be in the long term? So if I'm kind of projecting into the future, how good is it to be standing where I am right now, giving this talk, given what's going to happen in the future? This is typically a thing I've got to compute to be able to solve these problems. Okay, so let's dive into how we think about these things. As I said, the first problem is that learning is slow. And we all know this because we all spent like decades of our lives learning to become vaguely competent, which is, you know, the fundamental challenge of humanity. And this comes down to this idea that sample efficiency in something like reinforcement learning is terrible, right? You've got to try lots of things to figure out what's good and bad. If you only find out, you know, at the end of your life, if you made good and bad decisions, that's kind of hard to learn from. This is a tough problem. And then if you've got a robot that's trying to solve multiple tasks, you've got to learn about each one independently, which is obviously even worse. So what we need to do, and kind of a core principle in our work, is to think about how to transfer knowledge between different tasks. If I've learned to solve one task, that should make solving the next task easier. And there's a lot of different ways that we've thought about this, but maybe just to give an example, I want to show some work that actually came out of Steve's PhD that we did. And the idea here was like, maybe we can learn little pieces of knowledge that are reusable. And specifically what we looked at here was skills. So if you can learn something about skills, which is a small piece of behavioral knowledge, like a little mini policy that you could learn, if you can learn that, plus when to use it and what it does, that's some useful, reusable knowledge. So as an example, if you've got a skill in a little video game to walk down a ladder, and you can learn that the preconditions of the skill look like this. So you've got to be standing on top of a ladder, and the black area around here means we don't care what else is there. Then the effect is that you're at the bottom of a ladder, standing on some ground, and I don't care what the environment around that looks like. All right, so if I can learn these things, which we showed we can do, and then I get given a new scenario, all I have to be able to do is identify the places where these skills can be used. And then, as I'm wandering around, if I find that situation, I can just kind of instantiate that skill. Right? And that saves me all the trouble of figuring out what to do in these kinds of situations. And so we showed, for example, that if you can do that, then you can plan quite easily to solve fairly complicated problems with minimal learning, right? So if you've got skills for ladders, skills for opening doors and pulling levers, right, then you can solve new instances of problems with minimal learning. We even showed that you could do this in fairly complicated environments like Minecraft, right? Wandering around and opening doors and picking up objects, right? Problems that are really difficult over very long horizons that are hard to solve otherwise. Okay, so we can learn this kind of nugget of information that's transferable, but what else can we do? You can do other kinds of things. So this is some work another former student of mine, Ophir, did. If we can kind of do more than just learn about ourselves, if we can learn about the environment around us, we can reuse that information as well. And particularly here, what we looked at was kind of models of local interaction. So if you take a game like Sokoban over here, where you've got this little character that has to move around and push boxes so they end up on the little green dots over there. Right? This is a game that's existed for ages. Fairly challenging. And you get problems. Like if you push the box into a corner, you can't get it out of there. So how do you learn to solve these kinds of problems? Well, it turns out if you think more than just the agent, if you think about the environment around you, you can use this kind of information. And specifically, you can learn things like, if I've got my character and I push a box and there's nothing on the side of it, I can push the box. And if there's something on the other side, I can't push the box. Now, if you're in a level this size, you've actually seen every single interaction that's possible. Right? All you really need is two boxes so you can see how they interact with each other. But we showed you could do things like learn some rules about the dynamics of this environment, which can even be done in non-deep learning ways. You can learn like decision trees. That actually gives you enough information to be able to solve far more complicated levels. You can learn everything about the dynamics in these very, very simple settings that scale you up to far more complicated problems. Okay, so these are all examples of how you can learn little nuggets of information that you can reuse in this case in a planning setting to help you solve these larger problems. Okay, so that takes us some of the way towards kind of our grand challenge, but it doesn't get us everywhere, right? Because we've got these other two challenges I was talking about. The biggest one for me is that it's hard to define tasks. Like, how do I explain to my robot what I want it to do? You know, we can sit there and we can assign rewards to all sorts of different transitions, and this is complicated. This takes someone who really understands control, really understands learning, to kind of craft this whole thing and invest like a whole lot of energy into telling the robot what you want it to learn, which is kind of silly because then you knew it already, and we're kind of being a bit redundant about this whole thing. And there's a lot of like fine tuning that goes into this. You try something, you set some values, it learns for a while, it messes up dramatically. You go, oh wait, maybe I made that value too high and this one too low, and you do it again. And you end up with like reward hacking, where the thing learns how to do all sorts of terrible things you didn't intend because you didn't think it through properly. Another problem of being a human. So if we want to think about this kind of problem, how on earth do we set up the like reward structure to solve something like that? Right? Now, can we think about a more natural way of defining these tasks so that we can really do these elaborate, complicated things? That's a question we've been thinking about a lot in our work. So what we really care about here is we'd like to be able to specify a task in a way that's human understandable, so that like any human could specify this. Right? So for example, the kinds of things we might care about is, do X and Y simultaneously, or do X until some conditions met and then do Y? And you want to be able to do all of this without relearning the tasks every single time. And then finally, this should be like theoretically verifiable. Like, I don't want it to just randomly violate this, and if I've told it, don't kill all humans along the way, that it accidentally does that, right? This is suboptimal behavior, right? So if we can do all of this, then we end up with something that's general and safe. And this is work we've been spending a lot of time thinking about in the lab. This has largely been driven by Gerard's PhD, but many other people, like Steve, have been involved in this. And it kind of talks to this sort of story. So imagine you've got some sort of environment over here where you've got your little character who can wander around and pick up different kinds of objects. Now, maybe I've learned a value function for picking up blue objects. You can think of this as like being an overlay of this map. The higher values, it's like a measure of goodness. And so like being at the blue objects is like maximally good, and it decays away from that. That could be the thing I've learned. And this would be like the behavioral knowledge that tells me how to pick up blue things. And similarly, I could have learned a policy or a behavior to pick up boxes. Right? So if I've now learned these two pieces of information, right, we know from the previous work I was talking about that I could piece things together, but this is a different kind of piecing together that I care about. What I might care about here is to say, like, can I compose these two pieces of information without any further learning, and specifically thinking about a logical combination of this knowledge, right? So what I might want to do is say, like, I know how to pick up blue things, and I know how to pick up boxes, but what if I want to pick up something that's blue or a box, but not a blue box? Like, surely I should be able to do something like this if I've got that information already. So this is a question we've been thinking about a lot. And kind of the way we think about this is, let's say you've got these two different tasks, which we think of as two different MDPs. And each one's really kind of specifying different rewards. So the one we get good rewards for getting blue objects, the other one for getting boxes. Right, what I want to do is this kind of logical combination of this task knowledge that I have. Right, and if we think about this a little bit, like, we should be able to get some sort of algebra MDPs. We should be able to get an or a and or a not by doing kind of basic operations to this. Because that would be very satisfying. Then I can define these things logically to combine these different pieces of knowledge that I have. Now, the first thing we realize is when we want to do this, that they've got to have the same rewards everywhere except for at the goals. Right? It doesn't really make sense to be combining these things if, like, the one policy really wants you to trip over objects and the other one doesn't. Right? So we're typically now going to think of them as there's just different goals. That's going to be like change our reward functions, but everything else is going to be common. So can we just do this? Can we just say, if I had this knowledge to get blue things and this knowledge to get boxes, can I just get the and? And what was the and? Well, if we look back here, and corresponds to kind of getting the min. So can I take the min of these two bits of knowledge and just figure out how to get blue things that are blue and boxes? Well, it turns out if you do that, it doesn't work. It gives you these local optima that are very annoying. And we've looked at over the years many different ways of trying to solve this problem. But fundamentally, it comes down to the idea that, like, if you're hanging around in this part of the space, you don't have any information about this common goal, any information about what is a blue box. Okay, so in general, this isn't a great way to solve the problem. But then Gerard came along with some very clever solutions, which we've now kind of used and developed in a whole lot of different ways. So the idea here was really to think about how are these tasks related? And this is about imposing structure on this MDP, which is a very general object, right? So it can kind of encode anything in a class. But maybe that's too broad. Maybe we need very specific structure that we have to impose on this. And so what we thought about is, if we've got this environment defined by your states and your actions and your transitions and your rewards, then we can think about a set of, like, goals that we might want to reach, for example. And instead of thinking about our reward function as a function of state, action, and next state, we also condition it on goal, right? So we can take this idea seriously, that there's multiple tasks we might want to solve in this environment. And so we can actually encode that in there. We could say, well, why don't we just tell our reward function what goal we're going for, right? And be explicit about this. So what we basically do is we put a bit of structure into this reward function to say, if it's trying to reach one goal and it goes to a different goal, we're going to give it a negative reward and penalize it for doing the wrong thing. Other than that, we're going to keep the kind of reward structure the same. Okay, so if it gets to the wrong terminal state, then it gets a penalty. Now, this is kind of a small change to the structure, but conceptually, I think this is really important, that it's kind of really encoding, like, what are you intending to do, and are you pulling off what you intended to do? So if we make the small change to the reward function, we're then going to change some other things. So now, given this reward function, we now think about what we call a goal policy, which isn't normally a policy tells you, if I'm in a state, what action should I take? Now we also goal condition it. So we say, if I'm in a state and I'm trying to do a certain thing, what action should I take? Which again, I think is very natural because we're trying to do lots of things in the setting. And to get at that, the kind of big structure that we needed was to define something we call a world value function, which is, again, similar to the value function, but again, goal conditions. So now it's got a whole lot of information. It's a structure that thinks about the value of a state, of an action in a state if you're trying to achieve a certain goal. Okay, so we've now defined these kinds of structures. Well, we have to learn these kind of structures to give us the policy that's based on this reward function. And turns out, I won't go into it now, but we've shown that there's very efficient algorithms that we can learn these things, and they satisfy a lot of the same kind of properties that normal value functions satisfy. Okay, so if we can learn these things, what can we do with that? Well, so now we go back to the setting where we've got two tasks, which are MDPs. They differ on their rewards, but we also now have these world value functions defined for those two tasks. Okay, so now what we wanted was we wanted to be able to do this kind of Boolean algebra over our MDPs. But with our, what didn't work with our value functions now works with our world value functions. We can induce like this algebra correctly over these world value functions. Right, so with these changes, that we can do this. Okay, so having done that, what does this mean? Well, if we have two base skills, A and B, so we can solve two problems, and we can do this optimally, then we get these compositions A or B, A and B, and not A for free. Right, so zero shot. We don't have to do any extra learning to get them, and they're provably optimal. Okay, which is a big deal, because that gives us this kind of reliability that we've been talking about. So what's super cool about this is if you've learned some number of these base tasks that you've taken a lot of effort and time to learn, you get this like super exponential explosion in the compositions that come out of that just by like the definition of Boolean algebras, right? Because you can chain all these things together and solve those problems. And as I've said to you now, with no extra learning. So let's have a look at this. Okay, if we've got this kind of setup, what that means is if I have the blue and the box tasks, I can now get the blue or box task just by taking the max over these world value functions. So the different locations of where my character is, that's going to the closest thing that's a blue or a box, and I didn't have to do any extra learning for that. Or something that's blue and a box, I get that for free as well. Or something that's not a box. Or even do complicated things like an exclusive OR. I can just define that in terms of the Boolean algebra, and I don't have to do any learning as long as I know about these base tasks. And that's just super cool. So just for nice animations here, if I've spent a lot of time getting my little ant robot to learn how to go to the top, so these two top rooms, I've spent a lot of time getting it to learn how to go to the left rooms, then with no extra learning and operating kind of the whole stack from its low-level control and everything, right? I can go for the top or the left. I can go for top and left, so the top left. I could do the exclusive OR. I can do any of these kinds of operations, again, with no extra learning required. And learning was the big thing that was killing us at the beginning, right? The thing that takes our whole lifetime to do, we now get for free, like as long as we've got a reasonable set of base tasks. So what's really cool is that we're exploiting this idea of compositionality. But there's other things that we do compositionally, like in our lives. And that's language, right? So we communicate in a compositional way as well. And just for a dumb example, if I take like a very silly sentence, like I can replace like any of the words with any of a list of other words, and like I can make other grammatical sense out of this, right? So we can compose these different words in different ways, and like get this kind of super exponential benefit of composition through language. So this seems pretty natural. We got now this kind of composition in behavior. Can we exploit the composition in language to do some interesting stuff? Well, indeed we can. So this was some work we did with some people at ASU and Texas, UT Austin. So we looked at things like, can we take like a natural language instruction, pick up the red ball, plug it into like a transformer model, spit out the Boolean expression, and finally do our composition. And like we can show that kind of doing this sort of thing, you can actually even get it to learn end to end, that it gets better and better as it encounters more and more tasks. I mean, we used a kind of full kind of end-to-end system to look at this. We're still busy playing with different versions. This is a fun area to explore, piecing together these different kinds of technologies, where you can give it a natural language instruction and get it to kind of execute that based on this. And so you can see here some examples that have been done in kind of simulated worlds, where you can say things like natural language, go to the green chair or go to the red sphere, and it will figure out the policies that are needed to execute this. You can even do other things like think about other kinds of interaction. So particularly thinking to human-robot interaction, this was work that Jen did in her master's, right? We can take the fact that we've now got this kind of structured representation of the world and exploit this in different ways. So if you had your human says, bring me an object, right? Now, because the robot has some understanding of like these value functions and kind of where the modes are, the peaks in this distribution, like it can ask the correct kind of disambiguating questions. Like, were you talking about a ball or a box? And you'd say a ball. And now it still might have some ambiguity, which can resolve by asking the appropriate question. Which color? And you say the red one, and it gets the appropriate object. So doing this kind of thing, we can see that like asking the right questions a couple times, we can completely disambiguate like a task. So the robot doesn't have to spend a lot of time mucking around in the environment. It can kind of resolve all this ambiguity with a couple of the right questions. Whereas in kind of other work, typically you would point at the object to say, was it that one or that one? Now these things fall out naturally because we've got this kind of structure that talks about the different dimensions of compositionality in the environment. And obviously, because this is all about robots, I'm going to show this video, which you've already seen some of in the preview video before. And thanks to Pravesh for the animation of this, and I think Steve and Gerard and other people for spending all the time making this. So the idea here was, again, that you can spend a lot of time getting the little query robot to learn to kind of solve these base tasks around going to the bottom or going to the left, and then we can do these compositions with no additional learning, right? So go to the bottom and the left, and that just gets executed. Or go to the bottom and the left and don't use the door. Again, we'll see that coming out. So yeah, we can just specify these things in terms of the Boolean algebra, and like the behavior will be reliably executed. So go to the bottom and not the left, which would be the bottom right, or go to the bottom right, not using the door. And again, we can specify this in a very natural way. We didn't have to go and tinker with the reward function to get this kind of interesting behavior coming out. Another student of ours, Simon, showed that we can do this in kind of a multi-agent setting. So if you have here that like the red agent must go there, and the green agent to any of them, here the green agent over there and the red to any of them, and we AND these tasks, then we get kind of all the coordination and that sort of thing coming out of this for free, that they'll actually coordinate to solve the problem. And so we can look at this as a way of thinking about multi-agent or multi-robot coordination using the same kind of framework. So then, again, we want to see like what can we do with this? How far can we push this? So we've got a Yumi robot in our lab. And again, like there's a lot of learning that might be required here. So for the task setup here, we've got, this is a, the kind of setup only a roboticist appreciates, not real world people. But we've got blue objects placed over there, red objects placed over there, and then bins here that you might want to pack. So we could do a bunch of learning and learn a task that says fill the red bin or fill the blue bin, right? So we can do a whole lot of work to get it to learn those behaviors. Again, we think of those as the primitives. And then we can do these composition things on top of this. So what does a composition look like here? Well, we might have a task that says not red. So I want the red bin to be empty. Or we might want an exclusive OR that says I want either the red bin to be full or the blue bin to be full, but not both. And then these fall out naturally just by doing this composition again, which is very cool because this is now a wide variety of different tasks that are amenable, again, in a very natural, understandable way by using this kind of framework. All right, so these take a while, so I won't play through the whole thing. But then again, we wanted this problem. Okay, so this was the big thing that motivated us at the beginning, right? And so now we can do some of these things kind of in parallel, but how do we think kind of sequentially? How do we chain together these really temporally extended tasks where I know how I could do A and B at the same time, but now I've got like this ordering that I want to impose on this. How can we think about these kinds of problems? So we take this work even further and to think about like really the temporal aspects of this. So if we've already been exploiting like Boolean algebras, maybe we can do other things. And specifically, we looked at temporal logics or linear temporal logics here. And the idea is, let's say you have an environment, you can learn these skill primitives, right? These basic skills, right? We now might care about a task that's got some sort of more complicated structure. And again, here we looked specifically at temporal logics. So you can specify some sort of complicated structure. Now that can be translated into something called a reward machine. I'm not really going into the details here. We can talk about that later and you can read the papers. And this is kind of a state machine that describes the ordering of the tasks that we care about. So we can convert that from a formal definition into the structure. We can then take our skill primitives and this reward machine to create something, well, it's a planning problem, something we call a skill machine that tells you exactly what to do when to solve the problem. And finally, that will give you a zero-shot solution to the problem. So again, without going too much into the details, let me show you a bit how this works. So you might have some base skills that say, like I've learned a skill to go to a cylinder, I've learned a skill to go to a button, and a skill to go to what we call a hazard region. So I can learn these things in a standard kind of learning paradigm. But now I want to be able to piece these together. And using that framework I presented, you can do something that looks like this. So we could just piece those together using that system to say navigate to the button and then to a cylinder, right? That's just like a then specification. This falls out very naturally from the temporal logics. And again, with no additional learning, we get this kind of behavior coming out. Or we could say navigate to a button and then to a cylinder and never enter a hazard region. And this is important because this gives us some nice safety guarantees because we can say while never doing that. Right? So the whole time you're executing something, never do the unsafe thing. Right? And I think this is probably one of the big open questions in AI in general at the moment. How do we ensure that we never get our systems into dangerous states? Or something more sophisticated, navigate to a hazard, then to a cylinder, and finally to a cylinder again while avoiding hazards. So there it went to the hazard, went to the cylinder, and now to another cylinder while avoiding the hazards. All right, so we can now chain together these really long chains of tasks and again be guaranteed that they're going to execute in the way we want them to. And so finally, that gives us everything that we need to pull off this solution to this problem because I can specify this using a linear temporal logic. If I've learned the base skills, this now composes, again, with no further learning, for any task specification that I give it. And you can see here the whole time it's doing this, solving these problems, it's avoiding the delicate objects in the environment, it's finally doing the patrolling, right? It's doing everything I intended. I didn't have to sit there fiddling with reward functions to do that. So one last thing, we've now been extending this in different ways. So another student of ours, Tristan, has been looking at a different kind of machine, a counting reward automaton, and this lets us kind of count. So this is the kind of first demo of this to show that like if you took 3 of the first object, we want to make sure that you take the same number of the other objects. And so we're looking at this in different kinds of construction settings to make sure that you do the same number of things or keep count of like how you're solving different problems. So this is where we're taking this work at the moment. Yeah, so, I think kind of bringing this all together, what we really care about here is solving this kind of general set of problems. And we can leverage this this kind of additional structure that we can impose into our problems. In this case, we pose a bit of extra structure into our reward functions, and then we could do this kind of logical composition with some planning on top of that to really not have to solve each individual version of a problem, right? So that gives us this flexibility, instructability, and reliability, which is what we need to solve these kinds of complicated problems. And now as we're pushing more and more into like kind of the higher dimensional, the bigger robotics problems, this is going to kind of chip away at a lot of the painful, slow learning that's required, as I've shown in some of these examples, to give us these solutions like really quickly and really efficiently. So with that, I'll thank you and all the kind of countless people that have been involved in these projects. And I hope that was interesting, and I look forward to hearing about all your other projects as well over the next couple of days. Thanks.
Thank you. I think we'll open it up to the floor for any questions.
Really great presentation. One question. So in the final putting it all together, how long did it take then to learn? My assumption is you had to learn the individual tasks in order to build a fully temporal logic. How long did it take to learn and execute the task in terms of time?
So I mean, are you talking about the individual base?
Yeah, because you were right. So the one that you finally put together, you said you had to learn the individual and then you can then manipulate. So what is how we're talking in terms of time, like real world time in learning those tasks and then being able to execute the sequential learning over time?
So that's going to depend very much on the kind of task itself, right? So in this setting, in like a simulated environment, right, it comes down to kind of the diameter of the task. Like, if you were to solve some of these things like navigate to one of those points as a standard RL task, right? Again, that's going to depend. Like a small robot in a big room is going to take longer than a big robot in a small room, depends on the action space and so on. I think in these cases, like, again, the simulator ones, not that long. Now, there's obviously the difference in that we're learning these world value functions rather than the standard value functions. And there's some kind of tricks that go into that. But I think, you can think about it as like, let's say that you've got like the 10 base tasks, right? You'd kind of have to learn that anyway, right? If you wanted to solve those 10 things. But then if you want to learn anything that's like composed from that on top of that, right? You're now not doing that additional learning. So you've got this kind of essentially the same like overhead at the beginning. And what's cool about this kind of work is the more kind of these longer tasks that you have to solve, you end up kind of amortizing the total time, right? Because you're only learning that once off. So if I'm learning all of those base skills and then solving like one composition, I'm not really getting the maximum benefits out of this. It's like, we can now give this like ad nauseum new tasks, and it's never having to do the learning. Because the kind of, the key thing here, and we think about that kind of, those base skill learning piece as a almost, kind of the pre-deployment thing that it's got to do. Whereas like actually solving these tasks is really just a planning problem. So you've got to take the LTL specification, you've got to convert it into this reward machine, which is basically just the temporal state machine describing the kind of sequence of rewards. We then run kind of a value iteration type thing on top of that with the skills to give us the skill machine, and then we just execute that. And so that bit is really, really quick.
Follow-up question is how does it deal with perturbation? So essentially the robot's executing and then something random comes in, whether it's a human, especially if I'm more interested like the human robot kind of interaction environment. Human comes in and does something unexpected that kind of like puts a wrench into the process. How does this system deal with those types of perturbations?
Okay, so we haven't done a huge amount of exploring there, but you can think about the perturbations happening at like one of two levels, right? There's kind of almost in the base skills and then at this like composed structural level over there. It's going to depend, right? So if you're, the way like any policy would work, if you've got some navigation policy. If you did a perturbation that involved like nudging the agent to the side, like if it's running a policy, like essentially what it's learned as a policy is like a vector field to some extent, and it can recover from that. If your perturbation looks more like there's an unexpected obstacle somewhere and you've never seen something like that in training, like obviously you don't know what to do with that. And so for these kinds of things, you need to think about how you're like constructing your base skills. In terms of the kind of higher level composition, I mean, to a similar kind of level, if you've got like a, while something is true or until something is true, and you like change the current state of something, you can deal with this. It's when you leave, like kind of get to an out of distribution type state that is probably going to struggle there. But again, we haven't done much work in the space. That's just, from what we've seen, like the small scale perturbations.
Yeah. Thank you for your presentation, very insightful. So I'm very much interested in the concept of the office robot, where we have multiple instances or tasks. Maybe, for instance, like you said, fetching mails, delivering coffee, and so on and so on and so on, right? So firstly, I want to understand the pattern of execution. Let's say maybe does it start maybe with task A or task B, following the order that you maybe predefined also. And then I also want to understand that given that it can be maybe from task A to task B or both task A and task B at the same time. And then now I want to introduce the idea of priority. Like what if we consider, is it possible to employ priority so that maybe now let's prioritize delivering meals, or now let's prioritize coffee, given that dynamics can change, just can change, like how to take into that.
Cool, that's a nice question. And I think that's an important direction to look at. So, what's nice about this is if you're saying do A or B, right? What's nice is it's going to do kind of whatever ends up being more convenient in a sense through the composition. But, go to A or B, like if I'm close to A, I'm probably going to go for A, right? That's not really letting you tune a dial that says like, relatively how much do you care about them? We looked at this in a previous version of this work. We haven't been doing that much with this, where we could actually set like preference values over the different things you care about. I think that's a nice question to think about. I know Gerard's been doing some thinking in that direction. Yeah, maybe we can chat about that afterwards, because we haven't explored that a lot yet, but I think it is important to say like, do the following things, but I'd rather, if possible, you do A than B. Other questions? Yes.
Is there, during the learning of the primitive skills, do you notice like transfer? So is it like you learn one skill, then the next and the next? And then, so is there transfer in the subsequent skills?
So it's the setting that we've been mainly focusing on is like learning all the base skills together, which is like jointly learning them when you don't have like all of the like you don't have any pre-existing knowledge. It's like the standard setting we've been looking at. The kind of way the learning here works is that as you're moving around, you're actually not learning like, typically you'd think if you had to learn with respect to every single goal that it's going to be considerably slower because you've got to learn about all of them together. But it turns out you can like do the updates to pretty much everything simultaneously because you're learning about each goal in relation to the other ones. So that's kind of useful. I mean, that's not speeding it up. That's just not getting slower. There's other things you can do about like exploring relative to other goals and so on. So there's some techniques there for speeding it up. I think that the big thing would be if you then add in new goals later on, if you can leverage some of the information to do that. Again, that's not something we've explored yet. It should be possible, right? You should be able to exploit this knowledge and even bring in some of those other ideas that I spoke about at the beginning of like factorizing the knowledge in different ways. So again, I think that's an exciting topic to look at, which we haven't done much of yet.
So just want to thank you again. Thank you for a great talk. love to have. Right now, we're just going to take a little bit of a break as we prepare to stream to the ICRA at 40 conference at Rotterdam.
So we just need some time to
Switch over every.
It would be great if we could say something like that to a robot, but we can't do that. What we have to do is we have to say, rotate your hip by 4 degrees, and then rotate your knee by 9 degrees, and then your ankle by, it's just crazy. I don't know if any of you have ever played QWOP. QWOP is a really cool web-based computer game. And what you have to do in this game is you've got to get this guy to run. But what you've got is raw control of the joint angles in the thigh and the calves. And a game of QWOP pretty much always looks like the ones you're seeing. That's kind of what happens to that guy. Now, that kind of shows that it's pretty hard to do something like walking, right? If I were to say, we're going to do a long jump, that would be even harder. What if I tried to say, let's buy Coke? I mean, it's impossible to even conceive of learning to do something like that in this space, right? So what we actually want to do is we want to try to transform this problem into something more similar to what we do with a child, right? So we wanna actually create some high-level abilities. Button not doing the things. Okay, so if you're my age, you probably played this game track and field. Although most of you don't look like you're anywhere close to my age. That may be a problem. And in track and field, you had the same task. You had to do a long jump, right? But it was much easier here because you had a button that made you run. And if you pressed it faster, you ran faster. You had another button that was jump. And planning at this level is so much simpler. You just said, okay, I'm gonna run, and then I'm gonna jump. Now, the thing is, so what we're really looking for is we're looking for this higher level formulation, right? We're looking for skills which are useful combinations. Because if we can sort of group all the low-level actions that make up running together, we can then just tell the robot to run. Okay, and that's really cool. It'd be great if we could just do that with a robot. The problem is we don't know beforehand which combinations of actions are going to be useful, right? So if we have all of these low-level actions, all of these joint rotations, how do we combine them in ways that make sense? There's a potentially infinite number of combinations, right? So how do we decide that some combinations are good and some combinations are not? How do we discover these skills? Well, one thing we can do is we can try to observe behavior in the world and go, let's figure out what these skills are, right? We could say we're going to watch some actor in the world, and the actions that they do, we can say those look like useful things. Okay. But how do we know when we have them? When we picture that game of QWOP we had earlier, where the robot, or the agent on the screen, was just rotating its hips and its ankles and its knees. At some point, it might have accidentally stumbled across running or stumbled across jumping. But how would it know that it had? Right? It was just doing random things, and random things were happening in the world. How does it know that it ran so that it can shelve that and use it later? How does it know that it jumped so that it can use it later? That sounds incredibly difficult, right? But luckily, it's a solved problem. When you see something very difficult that's a solved problem, that's cool, because that means there must have been some really smart people who thought about it. Well, not really. We actually had some not particularly bright but looking people. That's my son. And one of the things that we notice in babies is that they very quickly learn goal-directed behavior, right? You guys all roboticists, robots are expensive. So if you happen to have a child, you would not be a real scientist if you didn't do experiments on them. So what I noticed very early on, so at this point he's something like 20 days old, was that he really didn't like Tigger. He was like, this is the worst. And So what I did was I put the tiger doll on his chest. Now at 20 days old, he's just flailing around. He's playing quack the same way you saw in the first level. But what's really interesting is that because he was motivated, he had some goal. I hate this toy. He very quickly learned to. I don't know if you guys saw the video earlier. I'm scared to make the clicker show it again. But what he very quickly learned to do was grab Tigger and throw it off of him. Right? So we know that when children are discovering skills, goals are important. Okay? So we're going to sort of take this inspiration and do that in our models. What are some other things that babies do? Well, one of the other things they're quite good at is mimicking. If any of you have toddlers, you know they'll incessantly mimic the things you say and do. And this idea of learning from demonstration is quite important because if you've ever tried to do any form of reinforcement learning, you'll know that you're generally just doing random things in the world and nothing useful happens. For almost the entire time you're learning, nothing useful happens. And then by chance, something cool happens, and then your agent will learn to do that over and over again, and that's great. What learning from demonstration can allow us to do is short-circuit this process, right? It allows us to say, okay, well, let's not behave randomly. Let's see some things that other people have been doing and do those. Another thing that we often observe is sequential composition. Okay, this is something that Benji touched on as well, which is where when you have low-level actions, what you can do to build up bigger things is you can chain them together. Okay? One thing that I found quite interesting was as the example of stacking blocks, which Benji had a cool video of a robot doing. I unfortunately don't have such a cool video, but I have a picture of my son stacking these blocks. What was really interesting to me when he started stacking blocks was he learned to construct a stack of size 2, meaning he could take a block and put another block on top, right? He never learned to create a stack of size 5. He didn't have to. As soon as he could make a stack of size 2, he could make a stack of size 5, right? So that's really interesting, is that he never had to learn the large task. Learning the low level or the small task of stacking 2 fundamentally had him learn how to put a block on top of another, and he could then chain that. Just zero shot. What's also interesting is that this idea of sequential composition, of being able to chain together various skills, could also be done by demonstration. And this was really cool. So when children are observing your behavior, they're able to already see the components and learn the component skills, right? For instance, if you're teaching your child to eat with a spoon, you had to walk to the bowl and maybe pour something into a bowl, pour cereal into a bowl, pour milk into the bowl, and then show him with the spoon how to move the spoon to his mouth. The child didn't think that all of this together was one task. The child could immediately see that there was a skill of moving the spoon to the mouth that you're trying to show them. And it could separate that from the rest of the information that it received. Okay, so it can do this sequential composition even when learning from demonstration. Did I just call myself it? Okay, well, there we go. So strategies that babies use for discovering skills. We talked about goal-directed behavior, learning from demonstration, sequential composition, and an important one is reusability, right? So what I mean by that is that if there's something a child is only going to do once ever, it's not gonna turn that into a skill, right? It's not gonna have some persistent representation of this thing that it can use over and over, right? So very important reusability when it comes to skills. So if we're trying to do this with a robot, we need to try and get all of these different things working in a computational setting. So we need to model goal-directed behavior, first of all. We need to have some way of telling our robot to behave like a child does and care about what the outcomes of particular motions are. And we do this using reinforcement learning, which Benji has outlined. What we can do with reinforcement learning is if we have some idea of a goal and we have some idea of consequences, so we have some system dynamics, meaning we know when we take particular actions, particular things happen. We can feed that to a reinforcement learning algorithm and get out a policy. So we can get some optimal behavior for whatever our goal is. For the purposes of this work, we're going to make the assumption, I guess, or take a view that skills are characterized by reward. So we're going to say something is a skill if it's goal directed, if it has an objective. Okay, we also need to do learning from demonstration. We also need to have some way of taking our observations and turning them into skills. And for this, we have what's called inverse reinforcement learning. Now, inverse reinforcement learning is one of those cases that I like in language where, if you know the word inverse, it gives you some very quick idea of what inverse reinforcement learning means. So you can generalize quite easily. In reinforcement learning, we said that we have goals and we have system dynamics, and our algorithm will give us a policy. Right? With inverse reinforcement learning, we just swap the behavior and the goals. So what we're given is we're given behavior, meaning we can observe behavior, right? We have samples from behavior. And we have the system dynamics. The inverse reinforcement learning algorithm can then recover the goals that were in those demonstrations. Okay. Importantly, with inverse reinforcement learning, it learns a single goal from a demonstration. What's important to us is we also need to be able to do sequential composition. Okay? So with inverse reinforcement learning, if we fit it a long sequence of states and actions, right? A long trajectory of behavior, it would be able to recover a single goal from that behavior. But that's not what we really want to do. We want to say, if I've got an unstructured demonstration, meaning I'm just doing a long behavior that incorporates many skills, we want to be able to recover the individual skills involved. So for instance, if I had a skill like making brownies, I think you'll be able to tell from the slide that I have no idea how to make brownies. But if we had a trajectory that represented making brownies, in there would be some sub-skills like pour water, mix ingredients, add milk, pour water again. Don't buy this. What we would want is a system that can take those trajectories and not just recover the global policy of how do we make brownies, but the policy of all of these sub-skills so that we can reuse them. Because later on, we might not be making brownies, we might be making pancakes, and maybe pancakes don't have the whole water stage in them. So the problem is that how do we segment this behavior? How do we take that trajectory that just has make brownies in it and turn it into a set of sub-skill trajectory? So the important thing is that we can't tell. We don't have annotations in these initial demonstrations of which skill is employed. So what we can view this as is we have some unobserved skill. And this unobserved skill is generating observations. And these skills are sort of chained together. So this looks kind of familiar. This looks like a hidden Markov model. In a hidden Markov model, we have those Zs up there, which are our skill chains, right? So at Z1 is the skill we're employing at time 1, Z2 the skill we're employing at time 2. But we don't have access to these. These are invisible to us. But those skills are generating our observations Y. Right, which are the things we can measure. And luckily for hidden Markov models, there are ways of recovering those initial skills. Because we're in the context of reinforcement learning, it's not a skill by itself that determines what our observation will look like. It's our skill plus our previous state of the world and the previous thing we were doing. Right? So what we have to do is instead use an auto-regressive hidden Markov model, where all we've done is we've added some dependency between an observation at the time step and observation at the previous time step, right? Basically, what this is to model is if I said, you're running, I couldn't figure out where you are, right? But if I said at the previous time step you were you are at position X and now you're running, then you might be able to figure out where you are. Okay, now one of the problems with this formulation, if we say we have this hidden Markov model of skills and those skills generate observations, if we're using this to learn from demonstration, the trouble is we can end up with some quite annoying things happening. One of the things we could observe is we could say that every little action we do is a skill. We could say rotating our hip joint by 10 degrees is a skill, and then rotating our ankle by 5 degrees is a skill. The problem with this is that we end up with the level of abstraction we were at before, right? We just change the name of our actions to skills. So what we really want is we want to think about some constraints we can put on our skills so that they are more reusable, right? And so that they operate at a higher level of abstraction. And so here we introduce some non-parametric models that give us some biases in our system. Now, what are these biases? What do we think we know about skills? One bias we're going to introduce is that we want skills to be popular. What does that mean in this context? That means we only call something a skill if we transition to it frequently, right? So something we do once off, we don't want to call that a skill. Okay, so we sort of take this idea that we're gonna reuse a skill. Okay, what that is, it's kind of a hack. We're saying skills are useful if they're reusable, but reusable is a hard thing to figure out. So instead we go, skills are useful if they're reused. So in our demonstrations, we say if a skill turns up a lot, cool, that's a high likelihood thing. Another thing we do is we say that if I've got a particular skill, there's probably some bias in the skills that it's going to transition to. When we looked at that hidden Markov model, we saw that we moved from a Z1 to a Z2 to a Z3 to a Z4. Is that random? If we're doing a particular skill, is the next skill random? Well, not really, because our demonstrations will generally be from some sort of task, right? So let's say we were playing soccer or something, and that's what our demonstrations are. We'd be way more likely to transition from something like running to something like jumping, maybe. Or if we're jumping, we'd be way more likely to transition to something like heading the ball, right? So the point is, we can say that skills don't transition randomly between each other, right? They transition in a biased way. Okay. Similarly, like if I were to look at something like soccer, when I'm running, I'm unlikely to stop and sign autographs. It's just not something that's going to be a very low. So I must have some way to model this. Another thing we need to consider is that different demonstrations could be of different tasks. Right? If you picture the case of the child, it's watching you all day. Sometimes you might be eating with a spoon, but other times you're just walking around or swimming or something. So we don't expect all demonstrations to encode the same task. We expect that some demonstrations will use some tasks and others will use different tasks. And furthermore, that within these different demonstrations, we expect the transition probabilities to be different. So if you were playing soccer, like I say, if you jump, the next thing you do might be to hit the ball. But if you're playing squash, that's super unlikely. So how do we model these? Well, if we want to introduce a bias where we transition to popular skills, we use something called the Chinese restaurant process or Dirichlet process. And how this works is that it sort of has a rich gets richer approach, right? The analogy in the Chinese restaurant process is that if you've got customers going to a Chinese restaurant, what they're going to do is they're going to sit at popular tables. So every time someone walks in, their probability of selecting a table gets higher for the more popular table, like based on the amount of people at the table. So you sort of have this sort of concentration effect where everyone wants to sit at the popular tables, okay? And you can think of every table as having a dish attached to it, so everyone at that table is going to get served the same dish, and that dish is our skill, okay? So the people are kind of like the transitions. When they go, they sit at a table, they're assigned a skill. popular skills are a higher likelihood than unpopular. The problem with this is that, like we said, different skills can have different skill transition probabilities. So instead, we changed to this idea of a Chinese restaurant franchise. Okay, this is kind of like we just have a lot of Chinese restaurants, and you go to one of the restaurants, and you end up sitting at the most popular table. But the dish that gets assigned at that restaurant, so the skill that we assign to the people sitting at the table, are drawn from a global distribution. That's really useful. That says that if I have a skill that's globally useful, if I have a skill that you do in almost every task you're demonstrating, so maybe my demonstrations are all of sports, then running is going to be super popular. Right? So what this allows us to do is allows us to say, yeah, running is super popular. You can all have different distributions at your different Chinese restaurants at different demonstrations, but running is always going to be super popular. The next thing we had to think about was that not all skills are in all trajectories. And to model that, we use an Indian buffet process or beta process. And how this works is that it's very similar. When you walk into an Indian buffet, you just choose a dish based on its popularity. Okay? And we use this purely to decide on skill membership in a particular trajectory. So our model says that if we had some demonstrations, we could assume that those demonstrations were from tasks that had skills selected based on a beta process or Indian buffet process. So we can select some subset of the skills. Once we have those skills, we choose the individual skill using our hierarchical Dirichlet process or Chinese restaurant process that we talked about, Chinese restaurant franchise that we talked about earlier. So those demonstrations have us transitioning between skills according to the popularity of those skills. And once we've selected skills, we have action selections based on reinforcement learning from the reward function that characterizes that skill. Okay, so this is our model, right? So we've got a model and we've got demonstrations. What we can do then is we can use some inference methods to figure out what our skills are. Okay, so here's where we get to the meat of it. So we've got a set of trajectories. And what we're trying to do is figure out which skills were involved in these trajectories, right? And we have some model for how skills work. So what we can do now is we can do inference by doing Markov chain Monte Carlo sampling. The first thing we do is what's called Metropolis Hastings sampling. So we start off saying, okay, look, let's just make a completely bad assumption. We have demonstrations. We've been watching some actions. Initially assume they're all the same skill. Right? So if my kid was watching me and I took cereal to the bowl and I poured it and I took the spoon to his mouth, he's assuming all of that is one skill. Then we make a proposal. We say, okay, let's take some random piece of this demonstration and call that skill B. Okay? So we've got some other skill in the middle there. Okay, utterly randomly. Hence the Markov part of it. We can now separate our trajectories into the parts we think are A and the parts we think are B. And we can do inverse reinforcement learning so that we get a policy that characterizes skill B and a policy that characterizes skill A. Right? Then we can say, okay, well, since I have these two skills, I can reassign things from my demonstrations into things that were more likely B. Right? So basically, I can go back and say, of all my demonstrations, here where I thought I was performing skill A, when I look at it now, it looks more like I was doing skill B. Okay? So I've now got a new kind of characterization of my trajectories. And then I say, okay, well, now that I know what skill A is, I know what skill B is, I know when I was doing skill A and when I was doing skill B, right? Or I think I know. Since I have this model that we talked about, I can calculate the likelihood of this being true and the likelihood of this being true. And then I can just pick the highest likelihood model. All right, so I can go, actually, it turns out this one looks more likely, so I accept my proposal. Or that one looks more likely, so I reject my proposal and B ceases to exist. And if I do this over and over again, I can eventually produce a high likelihood segmentation. So the things I can do is I can birth new skills like this one. I can kill skills, I can split skills, and I can merge skills. And just by doing this over and over again, I end up with some set with a characterization of my trajectories that looks good. So that all seems good in theory, but how do we test this? Well, so the first thing we did was we tested it in the car domain. How many of you have worked in inverse reinforcement learning at all? Okay, cool. So in inverse reinforcement learning, this is sort of a good benchmark domain. You have a car traveling down a highway, and it's got different skills that you can recover. So what I've done is the one on the left has got a policy where what it's trying to do is just hit every car. No, avoid every car. That one's the good guy. Right. Yeah, I think that one's the good guy. And the guy on the right, he's trying to hit every car. He's trying to hit every car. And you could also envision that there's other skills like you want to stay in the left lane, or you want to stay in the left lane and hit every car, by leaving the lane, or stay in the left lane unless you have to avoid cars, things like that. Right. So you've got all of these different policies. Then what we did was we generated trajectories in which the experts switched between these skills randomly. So meaning for some portion of the trajectory, it would try to hit all cars, and then we'd switch, and we go, okay, now I'm going to avoid all cars. And then we'd switch and go, now I'm going to stay in the left lane at all times, except if I have to avoid a car, and switch again, just random switching behavior, right? Because what we wanted to see is whether we can recover the switching behavior. So what I'll show you is, so on the top line, we've got our true switching behavior. So we can say the agent for a while was doing policy B, which was hit all cars, and then switch to policy A, which was avoid all cars, and then did policy C for a while, which was stay in the left lane but avoid all cars. And when we ran our recovery algorithm to try and figure out if we could see what skills were involved, we actually recovered the same ones pretty much. Right? So you can see that the split, there's some jankiness around the boundaries. Okay? And that's actually, there's nothing we can do about that. Basically, what that's about is that sometimes no matter which skill you're employing, you take the same actions. So it's impossible to tell which skill you're employing. So in the highway domain we were looking at there, a lot of the time the car just goes straight, like it doesn't change lanes, right? Whether or not it's avoiding cars or hitting cars. So we had some, but it turned out the system, we can recover the skills pretty effectively. What's also interesting is that if we behave according to those skills, we can get a reward of 37,000. If, on the other hand, we did the sort of default thing of just assuming that all of these are one skill, we'd get a reward of minus 14,000. So it's switching, having this skill switching behavior in order to model stuff is quite important. Okay, but what do we need to do to get it to work on robots? Well, one thing was we had to adapt it to continuous domains. So meaning, you have a continuous state space rather than discrete one. And we had to do some work on sample efficiency. And what we did there was we used a random forest-based factored transition model. That's a lot of annoying words. But fundamentally what we did there was we said, if you've got a robot, getting samples is expensive, right? Like you got to make your robot play in the world. So first of all, it's going to do dangerous things, but second of all, it just takes time. It takes time to reset your robot. So what we did was we fundamentally learned some form of simulator. You can think of it as a simplistic simulator for what the effects of our actions are. And then we can learn on that simulator instead of on the actual robot. Okay, we tested this in a drink making domain where we said we want to put various ingredients into a pot. And we used CHAMP at the CSIR for this. And again, we found very similarly that if we put particular skills in, or if the robot was acting according to particular skills, we could recover the original skills very, very effectively. So in this case, the skills were things like pour ingredient A into cup, pour ingredient B into cup, or pour ingredient C into a cup. Actually, I think it was lower level, and there was also go to particular ingredients. We didn't actually pour anything because I didn't want to put liquids on the robot. And then there was the one cup over there. This is the thing with robotics. I mean, you guys already know this, but one of the roadblocks on this experiment was that the robot kept just collapsing, and I just had no idea why. It would pick up the thing and it would just fall. And it turned out there was some bug in the compliance code where if it found something that it couldn't, if it found something too rigid, it would assume that for safety it needed to shut down. And so, like, a key component of this experiment was I had to put a sponge around the cup. So you can do all sorts of clever things, but eventually with robotics you end up putting a sponge around the cup. Okay, but so now we've recovered these skills. What do we do with it? The important thing is we need to be able to learn with these skills. Right? So we then, with Matthew Cockcroft, Steve, and Shahil Mochi, we worked on a couple of extensions. One was to getting these skills into a framework in which we can learn in reinforcement learning. Right? So we then used these skills to learn new tasks and work particularly well. Another thing that we experimented with was curriculum learning, and this was quite cool, where we said, if you've got demonstrations that encode only a few skills, and then you slowly build up the number of skills, how easy is it to recover these skills? Is it easier than if you have the full set of skills from the And it turns out, yes, it is way easier. So, yeah. So that's the end of the stuff I'm going to talk about skill discovery. I briefly wanted to mention some of the projects that I'm working on in case anyone is keen on collaboration, because I always tell my students that the key characteristic of a computer scientist is laziness, and I like collaboration because that means I can get you to do work instead of others. So one of the projects that I'm working on right now is called Culturally Sensitive Social Robotics for Africa with Prof. David Vernon at CMU Africa. And what this project is about is, one of the things we've observed with robots in human-robot interaction is that people react better to them when they behave in culturally appropriate ways. So we know this from research that was done in Cyprus, was one of the big ones. There were some done in Japan and some in South America, where if robots behave according to human cultural norms, the people that interact with these robots are just much more comfortable. But none of this research is done in Africa, where cultural norms can be quite different. The purpose of this project is to identify cultural norms under which robots would have to behave, and then come up with behaviors that suit these cultural norms. Then we're talking about things like, do people make eye contact? If you're talking to someone more senior than you, do you greet them with an honorific, or do you just use their name? These sorts of cultural norms. And we incorporate local languages as well, and then test these behaviors in larger tasks, right? So this is something that I think has quite important implications in Africa. And so if anyone wants to chat about it, please do. And another project that I'm heavily involved in is RoboCup with Brendan Ingram, who will be talking about RoboCup tomorrow, so don't miss it. But I think RoboCup would be a really great one to collaborate with some of you on, because one of the things that I think makes robotics research challenging in Africa is just the lack of community. We're all doing robotic things, but in very different environments. And when we participate in competitions like RoboCup, there aren't local players to collaborate with or even compete against, right? So in order to compete in something like RoboCup, it's necessarily a long flight and therefore infrequent. So I think that's something that I would love to get some other universities interested in as well. Okay, and that's it. Okay, are there any questions?
the IRL framework, how noisy or how sensitive is it to noise? Where if you have like a position in 3D space, there's infinite amounts of trajectories that could get to that. Like intuitively, I would all call those the same skill, right? Well, to get to this point, let's say. So just your opinions on that, like how sensitive it is.
Okay, so there's lots of different inverse reinforcement learning methods, and they sort of have different properties. But the key thing is that what they're trying to do is they're trying to figure out how likely it is that the demonstrations that you're observing came from that reward. So when there's some form of noise, especially if it's some sort of persistent noise, what will happen is that'll actually get incorporated into the reward function, even if you didn't really intend that. So basically how a lot of the methods work is they use the concept of maximum entropy. So what they're trying to say is that if there's any behavior that is displayed in a demonstration, it must be explained by the reward. Otherwise, everything else should be so what they'll do is that if there's some noise that's just noise, that won't matter so much. But if there's some consistent noise, what it will result in a reward function that's being recovered not being able to explain that noise. And so you'll end up with a slightly more complex reward function that will explain that noise.
And there's maybe just additional question. Have you seen this type of approach being used for like analogies that aren't related to like skill? So it looks like a clustering / segmentation approach. Has it been used to just categorize like sequences of trajectories in terms of other characteristics, not like a policy, but like something else?
I think the only example I have is I think your work did something similar with.
Yeah, that's why I'm curious. Yeah,
did something similar with
I didn't use IRL. That's why I'm curious.
Not with inverse reinforcement. But I actually think that, so I haven't seen it, but I actually think that it would be a very good approach, because the key thing with the reward function is that the reward function doesn't even have to be in the same space as the policy. So what that means is that you could, for instance, say that in my reward function, I have a feature describing something like aggression or, I don't know, what else, something that's not in our state. And we'd still be able to recover that coefficient in our inverse reinforcement. For a bit of context to everybody, I think what Brendan is referring to is like, let's say you're observing someone performing a particular set of actions. Could you say that the person that's doing those actions is maybe an aggressive person or a relaxed person or lazy or energetic, or could you have some properties that you think this person has? So I think inverse reinforcement learning would be a good way to recover that, because those dimensions that you're measuring don't have to be in the state space. So, any other questions?
Thanks, Pravesh. We have time for more questions, but I guess we'll move on to the next speaker. Okay.
Just give you 2 seconds. Okay, sorry guys, I think we'll just take about a 5-minute break, so you're welcome to go stretch your legs, get a bottle of water if you want, because we are a bit ahead of schedule now, so we made up quite a bit of last
Simulated instead of just accept it.
driver is picking up the gimmick.
Yeah.
The track hold.
I wonder if it would actually make sense. Just animating it to vision ECI. You cannot take you can animation of someone jumping.
You might actually end up.
Yeah. Then Brendan animation skills. So when you
the first time. Printed the air one for me.
Oh, you never
Typed with it.
You must have. It's more work than one. Oh my God, what are you looking at? You've got some. It's still not a song. People are subscribing.
I think I'm having photos of like my simulation. I'll just take a some lines. No, this is like
saves the motivation. Student doing it instead of you.
I think about like 19. I don't know what to do. I'll try to explain my whole point. I think it's all.
Is he still on? Way presents.
So like, Eamon's work has been like stuff that's out there.
It's just but also
I reckon we should get two students.
Like the light was like locked off and
things.
You can translate.
so you said
That's going back right and like
So professional seriously.
No, I can't.
I'm sure that
like refactoring, like here's a code base, refactor everything. Like see like
it's like just
So you should get two students next year. And you
that's who you are. So it's just like
it's a very simple thing. So use that as a way to say it's aligned to both.
That's never out. I looked at it, I said, I'd rather go to sleep together.
I mean, very simple thing. It's going to tie into both projects really.
Things could be are put in place to that. I don't have like a
one of the biggest reasons that like
actually you could just watch people.
I think I'm going to split.
that is very like hard to the skirt.
You're like conscious.
Could have been something nice and it's not got.
Okay.
I'm upset because I got the email like what to do.
Yeah.
Like ICRA.
But then when the lecturer messaged me,
Like videos are exciting. And I think I'm also excited. Me an actual.
I didn't even.
It ties into what you're doing.
in my mind.
You go with a dragon.
I think I'll probably
Maybe last.
yeah, literally the project like literally it's like one robot to teach itself, but then still find everyone.
double check. Otherwise, I'll probably
Yeah. I can instrument 400 cameras easily, then I'll distribute this. I think someone who's like comfortable with this.
When I done, I was like, I was trying to think how
It does like
get somebody to make it like a tree theme down, get a picture of my poster in the background. That looks
Avoiding it, she's like, oh, yeah. It was a distinction. I'm so excited about
Yeah, it's also like it's taking.
So she's writing a paper now.
You know,
Once
it's not like you're
which to
like it's more like AI.
Sign up for full presentation.
And so long as saying enforcement learning from it's fine. Yeah, but if I'm trying to
And they do like
learn the dynamics of it.
At least they're done.
So
Since you got it done in time.
yeah, exactly.
Let's say we had
all that stuff from the whole
we talking to small maybe pick up. Never known like where to tell it.
versus those kinds of
It's a little side box. I guess never done it. For that, of course, if let's say we taught it to do it, image capture the 3D reconstruction. I think we'd have to get the middle ground. Let's say it's faster to do it low quality. So maybe they can just dial it. Yeah, I don't know. I haven't trained, but figure out the subterranean. That's probably just object detection. They told it it's big.
You know, because I do.
I don't know. Go look at a rock in the wall. That's the probably a base of or something.
I had a feature space, but how was it?
Then you send it to photos, you have to find someone. The guy's like half his body's covered in with one object, but it's the object is like this isn't the human
like fields rather than actions. Like stuff.
A lot of mud on his face. No, it's not good.
So actually, maybe there's an way.
But also, I don't know if anyone
I'm sure people have, and like I'm pretty sure if you just import.
And Damien's
like
using my data, and I'm like,
For his
all the data we're doing it in service of Damien, so he needs to help me as well. Like I can't even
because he's been
it's such cool
optimization
yeah, exactly.
and reconstructing that.
Let's see you talk about it again.
He knows though. And please teach me because I have no idea. Yes. Once I've got
So I feel like with the TikTok control systems podcast, a casual system would be nothing compared to
Casual systems.
Do you need a flash drive?
I would love to see more.
Something's on a burn.
I'm excited about the social network. They should be invited. Such a
I think it was Mijou and just that's what I was saying. The problem, whole thing, sometimes.
Missed discussions.
Yeah, he hasn't missed a.
It's like 8 weeks. Let's get him. Let's go visit. You know what food
They would.
Yeah.
Didn't it?
Exactly. University. I made him once. We were trying to get fucking.
Yeah.
I'm sure it'll be fine. I haven't changed because
That was a tiny break because you're on display.
No.
Thanks, everybody. We're just going to have the last speaker of the session, and then afterwards we'll break for lunch. So I just want to introduce him. This is Gerard Nangatase. He is an associate lecturer at WITS. He just finished his PhD and is quite an integral part of the Rail Lab. His work is mainly in composition reinforcement learning, but I think if you want to strike up an interesting conversation with him, you should speak about artificial general intelligence.
Not yet. I thought it was you are. A lot of jokes are coming from this presentation. I don't want to kind of like spoil the jokes. Let's see. Good. Okay. Awesome. It's a demonstration of real-life robotics. To get to the point where AGI solves all of this first.
Did you just have no images on your slide?
Exactly, it was a presentation. Okay, perfect. So thanks, Janely, for the awesome introduction. So as she said, I am at Royal Lab at BIT with Benjamin Rossman. I'm actually finishing my PhD this week.
Clap, you were supposed to finish last week.
So Benjamin and Steve have been on my case since for the conference. And yeah, and I'm also I've been an associate or sessional lecturer in the department for a while and an associate lecturer since this year. So Benji already talked a bit about the whole composition work we have been doing. So I won't talk a lot about that. I will so at some point throughout this process, we were realizing that most of the work we have been doing has been setting up the theory of this whole composition framework and doing experiments in simulation. But ultimately, we want these approaches to be applied to real robots, right? But ultimately, that's what we care about. And so this was preliminary work we did to try to at least get steps closer to that point. So the work I'm presenting today is a collaboration of all of these awesome folks. Some of the faces you hopefully recognize. And the ones that you hear is Tamlin Love and Devon Jarvis, who are also members of the lab. Tamlin Love is now in Barcelona. And Devon Jarvis is also an associate lecturer in the lab. Cool. So as Benji mentioned earlier, we are ultimately interested in having multi-purpose robots, right? And the three key abilities we ideally want from them is flexibility, so the ability to solve multiple tasks in the environment, interpretability, so the ability to for us to be able to tell the agents what to do, maybe using natural language or formal language. And finally, reliability, right? And Benji has and this basically want to put some guarantees in the behavior we get from these agents. So Benji has talked about these 3 points. I want to focus on this reliability point, especially when we start considering applying these techniques to real robots. So this is what happens if you train an agent and then you want to do sim-to-real and directly apply the policy you have trained in simulation to the real world. What does this happen? So most of us have some familiarity with robotics, and we know how there is differences between simulation and real world, friction, the specific position of the walls, and so on. So this here is the forums domain that we did in simulation. We train our agent there, and then we just directly transfer the policy to a real life setting, and then it fails. Right? And so the first challenge is exactly that. Robot learning in the real world is hard, and so usually people want to train in simulation because ideally we should be able to create a high fidelity simulator. We train our we apply some of the sim-to-real approaches in the literature, maybe domain randomization and so on, to make robust policies, and then we transfer that to the real world. But clearly that fails. And and so that fails if your simulator is not high fidelity enough, or if there's some other change in distributions that you didn't anticipate during the sim-to-real transfer. So that is the challenge that we are faced with. And so for this project, we got basically 3 key ideas. First is that we want to be training our agents in a low fidelity simulator, because as most of us are familiar, for example, if you are doing robotics control, creating high fidelity simulators is very challenging, right? And not only is it very challenging, but creating it to such a point of fidelity such that your sim-to-real is going to work out is also very hard. So you want to train in a low fidelity simulator. For example, in this case, the real world forums domain has a turtle bot, continuous actions. The state space is also continuous. It's a continuous XY position of your turtle bot and the rotation. But in simulation, the idea that we had here was, let's discretize the state space, and let's also discretize the actions, right? And that way you can train in simulation using something like a tabular method of natural learning. And so, of course, this is not going to be enough, right? Because now our simulator is like very different in terms of like level of fidelity to the real world. But at least it's going to be very fast to train. The second key idea is that, let's say that we did this high fidelity simulation, and like I mentioned earlier, we're interested in flexibility, right? So the idea that we should be able to solve multiple tasks, but doing such training for every single task is impractical. Right? We don't want, when we want to ask our robot to do something, we don't want it to have to learn for every single task. So Benji already talked about this value computation idea that we introduced a while back. So I'm just going to give a brief summary here. And the main idea here is just that we want to train base skills in our simulation. So like in this case, for example, train how to go to the top rooms and how to go to the left rooms, and also how to go each door between each of those rooms. And then we can compose those skills to then solve any logical combination of them. So for example, if we want to go to the top room and not the left room and not the south door, then to the trajectory the agent will take, because we said not south door, right? And the agent is able to get the scale zero shot without further learning, using all of what Benji talked about earlier. Similarly, if we want the agent to go to the top and not the left, right? So to the top right corner. Cool. So we can leverage this computational ability to generate the skills in simulation to solve any task within it, as long as we can express those tasks using logic, using like temporal logic, essentially. Cool. And as Benji mentioned, this results in like a super exponential explosion of abilities. Okay, so that is how we are going to get our skills in simulation. Now, how do we transfer those skills in simulation to our actual real robot? So one idea here is because our skills in simulation were like macro actions, so we like had the simulation like go forward, go right, but the real robot has, so for the total bot, you can like give actions related to the torque you want for rotation, also like for forward velocity. But if you actually do that in the actual real total bot, in a rough environment, it is not going to actually go perfectly forward, right? Especially if it is like an old total bot. So you can, let's say, train that, like maybe use a small parameterized model to train that total bot to just like go forward in whatever specific rough domain it is in, and how to like turn at different angles. So you just train those low-level actions, and that way, if in simulation you have go forward, in the real world you apply the model you have learned for go forward, and that is how you take those primitive actions. That is the first key idea. Use macro-level actions in simulation, train those macro-level actions in your real robot. The second key idea is we want to leverage error correction, because in simulation, because we have discretized the environment, in the real world, when the robot takes like one step forward, for example, it's not necessarily going to arrive at the correct discrete position we expect it to be in. And so we want to apply some error correction. So maybe using like path planning of any path planning algorithm to move the robot from where it ended up in the real world to the position it expected to be in simulation. So the way we did it for the total body is just we had like a camera on top, and we had the blue and red color on top of the total body, and just use color detection to just determine both of those colors, and use that to calculate the position of the agent, the position of the total body, and its angle and its orientation. Cool. And then, given that we know those two, we can just perform simple path planning to move the robot to the position that it's expected to be in. So that is the second key idea. And so the general approach here, at least if you're trying to do naive sim to real, using this idea of training in a low fidelity simulator, is you train your base case, the low level simulator, you discretize your environment to match your low level simulator. You apply whichever position and orientation detection. So in this case, we just use colors to do that. but for a different robot, it might be different. And finally, we use that information to localize the robot, and at least in general, you can use SLAM for that. And then finally, we use that information to localize the robot in the real world and apply the policy we learned in simulation to the actual robot. That's the general framework. So what happens if we do this? So let's say we use that. So initially the robot starts at any random position. So this will kind of move to the initial state that is expected in simulation. So we use path planning to achieve that. And then from there, what if we apply the policy that we train in simulation? So the robot fails again. And hopefully it should kind of like make sense why the robot is failing, because the deviations from simulation and the real world is accumulating as the robot is progressing. And so eventually it deviates completely from what it expects to be in simulation. So if you kind of like do 5 trials, what we observe is like it fails like 3 out of 5 times. If you kind of look at the work clock time it took for the robot to execute this whole path, take into account getting the information from the simulator and so on, it was about 12 seconds. And this is basically just a measure in terms of pixel value between the final location it needed to be and the location it ended up at. And so what we observe if you just do direct transfer is that you get first execution, but success rate is extremely slow, and the accuracy is also very slow. It's also like very, very bad. Cool. So what if you kind of add error correction on top of this? Right? So because this is a result of deviating from the trajectory you expect at every time step, maybe at every time step, we can just do error correction to bring back our robot to the expected position. Cool. So if we do that, I'm not sure how to play videos on this. Cool. Let me get this, right? The correction at every single position on the trajectory. And so it is extremely accurate. Right? It has 35.5 success rate. It takes extremely long for it to execute this full trajectory. It gets pretty epsilon close to the goal that it needed to reach. And this is the amount of correction it needed to do to achieve that, right? So it is perfect. It is ideally what we want in terms of like accuracy, but it's extremely slow. So can we do better than this? So we have 2 extremes. On one extreme, we have trained our base case in simulation, we have done composition to generate any scale we need. And then we transfer that directly to the real robot, and it fails completely, right? So that was the previous one. In the other extreme, we, instead of just transferring the policy directly, we check the policy at every single step, check the deviation of the real robot from what is expected to be in simulation, and we do error correction at every single step. So that is the other extreme in terms of like accuracy and also amount of time that whole process takes. Now we have something in between where we have an accurate robot and safe in the sense that it doesn't cause like hit walls, but also fast execution time. So that is kind of like what we were investigating, and this is kind of the approach that we came up with. The idea is as follows. We are going to describe the trajectory that our robot is going to take. And in this case, we are using the turtle bot as an example, but you can kind of imagine doing this in like any modality of a robot. The only thing you need to determine is how do you localize your robot in the real world in terms of its states, and how do you perform your macro actions. So let's define the trajectory the robot needs to take as a series of scales, right? So for example, for the task of reaching this goal here, it needs to go to this door here, then go to the center of this room, then go to this door, and then go to the center of that room, right? So that is basically what this state diagram shows here. If you kind of remember what Benji talked about in terms of like the temporal logic composition, we can leverage that work to generate the scale corresponding to this trajectory, right? In this case, not much composition is happening here. Very straightforward task. But in general, any one of these paths here can be a logical composition of primitives. Cool. And so what we are going to do is we are going to do error correction at these macro levels, at these high levels, right? Not at every single time step, but when the agent reaches each of these bottleneck goals, right? And so if we do that, what do we see? So error correction to get to the initial state, the error correction at only the bottleneck state. So if you play that again. So it gets here, it goes to, so this one was very fast, that's why we didn't notice it. But here and here, hopefully we noticed that was doing error correction at each of those points. So if you kind of look at what we get from that, so again, high success rate now, the average time it took to kind of like execute this whole thing is that long. If you go back to the, oh, actually I can do that. Okay. Same one. Actually, no, this is the one. So this is the direct, this is the one where you kind of like get your compositions and you do the error correction every single time. You go do the error correction at the bottleneck state. Yeah. So only error correction at the doors, at the center of each room, and you get much faster execution time. The success rate is still high. The average time it takes to execute the whole policy is extremely fast. The average distance to the goal is epsilon close to the goal, so pretty accurate. And the number of corrections is dramatically lower because you only do error corrections at your sub-goal levels. So that is essentially the preliminary work we did here. One thing I didn't show here is all of the hours and days it took to set up this whole domain here, get the discretizing to work, get this error correction. So you'll be amazed by how sensitive, I guess some of you are familiar with this, but like how sensitive the camera is to lightning and how that affects these colors. And so we spend centuries kind of like manipulating the colors to get the correct positions. Literally one day, we spent the whole day to get one of these videos. We were outside one of the buildings in this stadium. We spent like the whole day getting the video, and throughout the day, as the sunlight is kind of like changing position, the colors on the stuff was changing, and so we were having to recalibrate our color detection to account for that. So it's a lot of work to still be done with respect to this, but I hope the key idea at least was conveyed. So let me just summarize this whole process. So the general idea we came up with is, given any kind of like robot that you have, here's at least what we propose, and I kind of welcome any ideas that you guys have with respect to this project, because this is something we kind of want to continue, and also like test this in different modalities of robots. So the key idea is train primitive scales. So like these are low-level actions in the real world, because that is going to be very fast to train, right? Like how to go forward, how to pick up a cup of coffee, and so on. Then train low-level tasks in your simulator, in the low-fidelity simulator, using those macro-level actions, right? Then you can compose those low-level scales you have learned to solve any logical combination of them. Then you can express the task you want your robot to solve using temporal sequences. So you can imagine getting this from any language instruction, like linear temporal logic or like regular languages. And this is the step at which you want to do your error correction, not at this step here, right? And so using the curve composition work we did, these temporal sequences, you can get the scales for them by using the temporal logics, the zero-shot temporal logics work that we did. The logical composition, you can get the corresponding scales from them zero-shot, which is the very composition work we did. So this is the only thing you need to train in simulation, these low-level tasks. And this is the only thing you need to train in the physical system, your primitive scales. And yeah, so that turned out to work decently well for us. That's pretty much it. Thanks for listening.
Thank you very much. Any questions?
I have a question regarding the color calibration thing that you mentioned. I understand how hard it is. Why didn't you go for QR code or something?
So we tried that, and you'll be amazed by how sensitive QR code is to the blurriness of the picture and the distance to the camera. So this we by far throughout this whole process, this localization of the robot and the orientation of the robot was most time on. If anyone has like any ideas for doing this, not just for a little bot, but for a general robot, that would be something that would be nice.
The Kita does from a master's.
Nice. Awesome. And there's no other questions. Thanks.
Okay, thanks everyone. So that completes our robot learning session. We're now going to have lunch, which is just where we had coffee this morning. Okay. Please be back in an hour so that we can continue with the next session. Thank
Installation to the Oh, so like that was I see like it was so like you have like 3 time scales here. Your time scale is like what you're actually executing. So this is for that simple. Your agent is actually simulation. What you do
Thank you. Slots. Two really interesting talks, mostly looking at leg robotics. Firstly, I'd like to introduce Dr. Cullen Fisher. Cullen is ANIAC's Africa Research Chair in Mining at Mining Robotics at Stellenbosch University. He's a member of the Electronics and Systems Lab there. He's a senior lecturer. Cullen and I actually did our undergrad together in this area.
Welcome, everyone. So like Paul said, I come from Stellenbosch. I'm going to give you a talk on just some of the basic platforms that I've worked on over the last few years. Combined a lot of research from UCT as well. So there'll be a little bit of overlap with Dr. Shield's presentation after mine. But yeah, I'm going to give you a quick overview of myself and my research lab, then go into a bit of the history of robotics and sort of my history with robotics, looking at a bit of cheetah inspiration, looking at some of the stuff I did in my undergrad, and my master's, and my PhD at UCT, and then what I continued with at Stellenbosch. And then start quickly talking about mining inspection robotics, which is potentially not legged robotics, but you can use legged robotics, so it all still fits. So about me, I got my PhD at UCT. This was my final year project where we started a platform with a tail to really write itself, and that sort of started my trend in robotics with bio-inspiration with my supervisor, Amir Patel. I currently focus on a bit of legged robotics, mainly autonomous vehicles, a lot of mapping of environments, robust control. Currently senior lecturer, and recently started a research chair position that started at the beginning of this year, and that's with a blasting company actually located in Joburg here, so I'm here quite frequently. And the aim of this project is to start upskilling students, particularly in AI for sort of autonomous inspection, a lot of trying to improve safety conditions in these underground mining environments, and basically trying to create accurate maps of these very hazardous environments that we send people into. And so this started beginning of this year, and it's a project. So I come from the Electronic Systems Laboratory, and we have quite a few academics. We have a recent addition, Li Jun Zhang, who joined us in September, and we focus a lot on autonomous vehicles, robotics, and space systems. So we actually started out as a satellite research group, and we have to date launched 2 satellites, which were big monsters, but now we're focusing more on CubeSats and the robust control of them, working with a lot of companies in and around Stellenbosch. And we offer quite a few short courses and ground stations and facilities for satellite research. We focus a lot on robust control, so a lot of drones swinging payloads, a lot of control, landing on moving platforms. So there you can see a bakkie with a trailer, a lot of automation. And we try and do these algorithms that are platform independent, that we can try and use same techniques for different platforms. We also pump a lot of effort into F1/10th racing, so a lot of AI, sim to real transfer stuff, and trying to get AI to drive these platforms and then throw obstacles in their way and see what happens. And recently, the research group has started pivoting into underground mining robots, and just pretend that that's a legged robot, and then it all fits into it. So just some basic history of robotics. So basically in the 80s, I consider Rayvid as the sort of the father of legged robotics, and they came up with this amazing platform that was just far ahead of anything that we've even thought of. And they did all of this with a very, very simplistic controller that looked at maintaining hopping heights, looked at maintaining the body attitude, as well as hopping speed. And this controller sort of revolutionized robotics in my very limited opinion. And the controller is very, very simple. So you have three different concepts that you are trying to address, and there's a little very, very simplistic controller for each one. So here you determine how much force you actually want the leg to produce, and that is look at the desired height that you want to get to, look at the height that it was, times it by a gain, and you have this very, very simplistic controller to generate a force. Then if you want to start addressing the body attitude, you kind of do the exact same thing. Here you have a little PD controller. So again, very, very simple controller. So one generates a force, one generates a torque at the hip, and from this you gain majority of your effects, and then when the robot's in the air, you decide where you need to place its foot. Okay? If you want to increase speed, you place it slightly behind the desired point. If you want to decrease speed, you place it slightly in front. So very, very simplistic controllers with basic, PD type controllers, very easy to run. And with that, we generated these robotic platforms. And the nice thing with this controller, which sort of helped a lot of the early robotic platforms, is that works for a monopod. If you have a biped, you just offset the phases. If you have a quadruped, it's the same as having bipeds, which is the same as having 4 monopods. So this controller scaled really nicely and allowed us to control these platforms in a very, very simple, easy way to do. So that sort of like got me into robotics. And then with my supervisor, Amir Patel from who's recently left now, which is quite sad, we started looking at a lot of inspiration. I'm not going to go into too much detail of this. I'm pretty sure Dr. Shield over there will give you far more cool stuff. But in the beginning, they focused on studying the cheetah with just a single sensor on its collar, and we didn't get a lot of information about what the cheetah is actually doing. And we wanted to study it a little bit further to see, what is its spine doing? How does it accelerate? How does it decelerate? And start getting a better idea of how this animal moves, and can we actually apply it to robotics. So part of my master's and then subsequent projects afterwards was to start tracking the cheetah's spine and tail. So Amir and I did a whole bunch of simulations where we tried to model the spine, model the tail with rigid kinematic links. We got cheetah fur that I had to sit in a wind tunnel with rotting cheetah fur. Doesn't smell nice. So that's actual cheetah fur. We didn't kill the cheetah. It died naturally. And we started looking at filming these cheetahs, trying to study the motion, seeing how fast they flick their tail, what is the tail used for, so you can see how that tied into my 4th year project, and start looking at what aerodynamic effects it has on it and bring that into our model. We also went further and put on a harness on the cheetah with backwards facing cameras to go and track the motion of the tail and to see how is it using this tail to achieve its motion. So how is it using it during acceleration, how is it using it, and trying to generate an idea of what torques it's actually imparting onto the body. Here you can see very high speed run, very difficult to track that quite accurately. But that got me thinking, that cheetah jumped out of that bucket and just started pacing it up. So we started looking at how do these legged robots accelerate? So what is the optimal way of acceleration? So I generated a whole bunch of trajectory optimization results for a long time horizon and looked at different cost functions to see how are these platforms actually accelerating, and does it tie back to nature? So here you can see there aren't any intermediate gates. It launches straight up into the gate at once. If you have a different cost function, then it will kind of walk at the slowest speed, and then as soon as it needs to rapidly accelerate, again, it does this massive jump straight up to its optimal velocity. So when we accelerate, intermediate gates don't really matter. If you want to get to a gallop, just jump straight into a gallop and go. You don't have to go into a trot or a bound first. I did extend this to quadrupeds and taking it further, but it's a very long, slow video, so I'm not going to play that. And you can see the exact same thing with deceleration as well. It stopped and then walked a bit. So that was part of that, how do these platforms accelerate? And we looked into the different gates. Then I started looking into sort of what is the optimal spine morphology for these platforms. So the large part of my master's was to simulate a whole bunch of different robots with a prismatic spine, a rigid spine, and a revolute spine, and then ran a whole bunch of Monte Carlo simulations for months during student protesting, which was great because that's all in the computer lab. And from that, doing bootstrapping results to try and determine which is the optimal spine for these very aggressive acceleration maneuvers. And it turns out that prismatic spine is great for rapidly accelerating. Same for decelerating, because it can sort of absorb all the energy. Again, I worked with another PhD student under Muir supervision, and we started looking at leg bend direction as well. So again, 100 robots, 20 trajectories, bootstrapping results, determining should the knees point inwards, should they point outwards, should they point forward, should they point to the back. So trying to get an understanding of how should we accelerate, which was quite a cool result. So just some platforms that I've worked on. So back at UCT, we developed a bipedal robot here, which was built by one of the master's students that I helped out with. And we managed to get this robot machined, built, hopping quite nicely. Also using a Rayboat controller. So the nice thing with that Rayboat controller, we can take it, generate our trajectories that we need, and then we can map it to our coaxial motors on sort of our scissor leg and make it hop. So that was quite a cool platform. Quite nice for our lab back then. It was like our first big robot we had built and got hopping. So that was quite exciting. I thought there was a video on it, but there wasn't. Then that led into my PhD, where I started looking at using trajectory optimization to inspire robotic design. So everyone comes up with these brushless DC motors, but we wanted to see sort of what is the optimal morphology for our robots, what naturally emerges. So again, I did a whole bunch of trajectory optimization stuff, and it turned out you need very accurate foot placement, but when you generate that force to hop, you need a very explosive force. So I developed this platform here with, again, another master's student, where we had a nice brushless DC motor to actuate our foot so we could get accurate position control of the foot location. And we attached a massive pneumatic actuator to it. So that will give us our nice explosive force to launch the platform into the air. And it worked. Then I went to Stellenbosch and left UCT after, feels like 100 years, but it was only about 11. And here we again generated a trajectory optimization stuff. And we started focusing on going from a nice rigid terrain to a sort of terrain that your foot slips on, it penetrates, it's, you know, and designing one controller that can robustly control it. We did that. I then kind of moved away from pneumatics because attaching a massive pneumatic cylinder to a robot is a bit difficult. So we developed a bipedal robot as well. John, who said I can't say this, but who refuses to do PhD with me, will be presenting this tomorrow. So I'm not going to touch on this too much, but we looked at designing nice MPC controllers to make it walk. So the idea for this project, sort of where it's going, is we're going to take that biped and we're going to do what Rayboat did and strap another biped to it and get it to start walking. So the next step is to create our quadruped and just get it doing some nice walking maneuvers for us. So for some of this research, I took it a little bit further and I started looking at generating accurate friction cones to map this. So often a lot of the stuff we do in trajectory optimization is still 2D, and then you can get a very accurate representation of your friction cone. But often people make a nice approximation of your friction, so you either over or under represent how much friction you actually have. And if you start looking at how these robots accelerate, how cheetahs accelerate, you will see that there is often slip. So having accurate representation of friction is very important because you are going to be pushing platforms to their limits where they will slip. So using a ton of complementarity constraints and an absolute nightmare of maths, we were able to actually generate a nice cone representation of our friction so that we can bring that into trajectory optimization and get accurate representations of friction for these platforms, so that when we start looking at turning maneuvers, rapid acceleration, rapid deceleration, we can push these robots to the limit, and we don't care if they slip because we have a relatively accurate representation of it. Otherwise, you need to make sure that your robot never reaches slipping conditions because you don't know what will actually happen. And then in our lab, we've just picture this running nice and smoothly and the robots moving. We've built a bunch of other platforms that we've done some tests on. So on the left there, we have a platform using linear actuators. So incredibly slow, but when you lose power, it doesn't just collapse to the ground. It just stays standing because it's linear actuators. So it can also carry a ton of equipment. I think it can carry about 40, 50 kilograms without worrying. And then to drive around, the feet are actually wheels, so it can just drive like a normal car if you need speed. Then we also do a bunch of research on sort of hexapod spider robots using just servo motors. And then we also do technically that's a legged robot, but that's cheating a bit. Yeah, so we do have these platforms that we are pushing out some research as well. So what the future holds, when Paul and I were in undergrad, the idea was to build these platforms. They weren't available. Everyone was building their own platforms. That has drastically changed in the last couple of years, where there are actually commercially available robots that you can just buy and do research on, and they are slowly getting cheaper and cheaper and becoming more economically feasible. Some of them aren't brilliant, but it does open up this possibility where we can actually start focusing application-based research instead of pumping out master students, rebuilding a platform that isn't as robust as something else. If you look at companies like Unitree, they're releasing a lot of bipedal platforms that are relatively cheap. They have a lot of quadruped platforms as well. So I think we are starting to shift towards more application-based research on these platforms instead of back in the day where it was designed from scratch and build this platform. And there you can see how they have evolved over the years, and it's quite incredible to see how far we've come in such a short time and how much abuse our robots have taken from. So with that sort of shift to application-based research, I've also sort of shifted to more inspection-based robotics. So I'm moving away from building these low-cost platforms because in a South African context, that's not really feasible anymore. So beginning of this year, I was appointed as a research chair in mining robotics. And there's a company that is pushing, so NEX is pushing a lot of AI development in robotics with a focus on underground inspection. So looking at trying to map these very, very hazardous, very bad conditions, especially in South Africa. They're a lot worse than other countries, and trying to improve safety. So trying to predict things, trying to help out our miners to keep them safe. So a trend in South Africa is we are continuously going deeper and narrower, okay? If you have a 1 meter high reef that you want to mine, you are going to make that tunnel 1 meter. Okay? If you make it 2 meters to make it nice and safe for the human, that's a lot of wasted explosives, a lot of money down the drain, and companies are not doing that. So they're going deeper and narrower, trying to avoid waste and following how thick that reef is, which is very hazardous for our mines. However, there is an ever increasing demand for it, so we keep sending people there. So we are looking for trying to map these environments, and currently that is a very labor-intensive and very manual process, and we want to try and automate that, bring in robotics to make sure it is safe for people before we send people in to do that. So NEX has a saying that they want to humanize mining. So after a seismic activity, you don't want to send a human in there. We want to send a robot in to make sure it is safe to send humans in there. If there is a collapse, which unfortunately happens quite often, then we want to send robotics in to see, can we get these people out instead of sending more people in to get trapped. and a company that we frequently work with, Docking, they say don't send a human to do a machine's job. So that is really what we are trying to push with this chair. So currently, we send a lot of people underground to do very manual inspection, a lot of visual inspection. It doesn't work too well. We have remote sensors, and it doesn't work too well. You know, with remote sensors, you're not getting that resolution of data that you need. We do have some inspection vehicles, but they're manually operated as well, very time consuming. So an important thing of why we need to do this is we're in a continuously changing environment that we are blowing up. So the chances of something going unstable and collapsing is very high, considering we blow it up every night. So we need to start detecting loose rocks, sagging walls, and fallout ground to try and improve safety for our miners. And one reason why this is very important is because in 2002, 9 miners were nearly killed because they had old maps of an area. They drilled into an abandoned mine that they didn't know was there. That mine was flooded. Therefore, their mine became flooded, and they were trapped for 77 hours. And they had to go and try and pinpoint where these miners were, drill a hole down, and pull them up. Okay. So if we have accurate maps of our mines, when things like this go wrong, we know where our people are, we know how to get them, we know where to drill. So that 77 hours could have been drastically reduced if we knew all of that. So the problem with these underground environments is, you know, if you're trying to map this building, you have nice straight walls, everything is nice, you know, it's predictable. However, we're in sort of natural caves, we're in caverns, we're in disaster areas. You can't predict any of that. So now we're trying to develop algorithms for our robots to actually go and explore these areas, to try and map them and get an idea of what's happening there. So if you go and watch some of the DARPA challenge stuff, I'll show you a video about it just now. That's a very nice mining environment that they were in. When I went to Impala Mines, this is what it looks like. You can see there's people sitting here. So this is under a meter high, people sitting under it. There's cables everywhere. There's support bolts in the roof. It is a very, very bad environment. Nothing is smooth. This is considered a nice smooth path for the robot. So it's very difficult to try and develop these algorithms for these platforms to go and explore. So there's just an idea looking around, you know, there's things moving, there's support pillars everywhere, the ground, there's nothing smooth. You can see it is incredibly dark. After a blast, there's a lot of dust that has been popped up into the air. You can see the ground is sort of a grinding paste with a lot of metal deposits in it. This is considered a smooth tunnel, cables and jagged rocks everywhere. There's water on the ground. There's steep slopes. So we need to develop platforms that can navigate this environment. So steep slopes, small areas, no paths to follow, so a lot of open areas. So it's not just go down a tunnel, it's a wide open area that we need to map and explore. And then there's no communication underground, okay? So there's a lot of metal deposits in the rock, so communication doesn't really work under there. Also, you blow it up every night, so infrastructure down there doesn't last. No GPS, and because you're blowing it up every night, the map changes. So every single day you have a new map that you need to go and figure out, is it due to a collapse or is it due to you blowing it up and getting an advancement? So there have been some developments in this field for robotic platforms. So ENIAC has developed this underground autonomous truck, but it is more semi-autonomous with some teleoperation. And they're trying to bring their miners away from the stope face, which is the most dangerous area, and sort of do autonomous priming stuff and you know, keep our miners at a safe distance. And the problem with this is big, massive truck works great in big overseas mines. It doesn't really fit in the South African context. So the idea is, can we take this and can we make it smaller? Can we put it onto a small robotic platform to go and do all the inspection and path planning and mapping for it? So there have been some inspection robots that have been developed of tracked, wheeled, legged, more legged robots, do this underground inspection stuff. But the problem is the physical properties of the robot define where it can go. So if you have a legged robot, it can't go everywhere where a different platform will go. You know, a drone will maybe have the ability to get to areas where your legged robot can't, but your drone will probably only fly for 10 minutes before running out of battery. So there's a lot of trade-off here, and that results in sort of teams of robots trying to tackle this challenge. So you can send your wheeled robot as far as it can go, then you can send your tracked robot, then you can send your legged robot, then you can have your drone for that final area. But the problem is with teams like this, other complications are you need to share a map with them, they need to communicate with each other, you need accurate maps for them. You know, do you have centralized, do you have distributed, there's no communication. So that becomes incredibly difficult. But DARPA has said they've sort of solved this challenge, but that mining condition there doesn't quite look like a South African mine. And a lot of what they're focusing on is sort of exploring tunnels. So just doing the exploration of the mine, walking down tunnels. So brilliant research, they're miles ahead. They're doing some really, really cool stuff, but doesn't quite fit into our context, which is, you know, scanning this open area. And particularly looking for loose rocks, hazard conditions, whereas there they're just doing a map of the area and trying to find artifacts. So the problem with robots is they need to do a whole bunch of things. You're going to have a ton of different sensors on them. The sensors are going to get dusty and dirty, so they need to either self-clean. You need to try and do perception to see what's around you, which is quite difficult. From that, you need to generate path planning and mapping and low-level control. Now you have a robot team, so you need to communicate with the rest of your team to see where to go. So very, very challenging project. And with this environment, we get a lot of sensor degradation. You know, it's very dark. There's a lot of water. You can't rely on odometry because your robot's going to slip everywhere. There's no distinct feature. I've walked down a 3-kilometer tunnel. It all looks the same. Another problem is you're not on very even terrain, so you have phantom objects. So if you're going down a slope and you come up, your LiDAR is going to detect that as a wall, but it's not. It's just a valley that you are going through. So there's a lot of problems that you need to overcome. Very dirty environment, so you need self-cleaning cameras, self-cleaning sensors. Yeah, and then from this, we start looking at, you know, what is everyone doing in robotics? So a lot of people are focusing on 2D mapping. Some of them are focusing on 2.5D, and that's basically the difference. But again, we can't rely on this. If we have a 1 meter high roof, we can't rely on a 2.5D map because we might hit the top. So we have to focus on 3D mapping. Now the problem is there's no communication, so you have to do everything on board. So data processing becomes very, very intense. Just even storing this information becomes very, very challenging. If you have a team of robots, you need to share that map, which is also quite difficult. So then with no communication, there's another thing we need to decide. Do we go full autonomous or do we go teleoperated? Okay, full autonomous is great. We don't need to worry about many things, just send them off and let them do their own thing. But that is quite difficult in this environment. And if we need real-time information from these platforms, we need a communication network. If we have a teleoperated robot, we need a communication network. Otherwise, you may as well go sit on the robot or just not have the robot and go in the mine. So a lot of people have started looking into sort of having these, just think of this as a legged robot. So they have these nodes that they go and deploy to form this mesh network for communication. That's great for the DARPA challenge. You have an hour, your node has to last an hour. Brilliant. Great for search and rescue. Miners were trapped for 77 hours. Okay, your sensor needs to last 77 hours. Doable. But for daily operation, doesn't work too well. You know, mine is not going to send in people to go and replace a battery on a communication node every single day. It's just not going to work. So we need to come up with different ways of doing this and different methods. Again, I'm not worried about all of this. I'm worried about exploring this vast open space. And you can see what they've done in DARPA. They're mainly focused on exploring tunnels. So we don't have a path to follow. We have a massive open area that is not smooth. So we need to start doing like terrain-aware navigation. So my approach started beginning of this year. I have a team of 5 master's students. Lauren actually decided to do PhD with me, so she's going to start next year. So we're focusing more on the algorithms. We're not too cared about the platform, and we're not caring about following a tunnel. We want to be in an open area. The robot will live in that open area, and it will just continuously map that environment to make sure, what has changed. Is it change due to a blast? Was it change due to the roof about to collapse? So very, very complicated system with a ton of different sensors. We've got LiDARs, thermal cameras, depth cameras, normal cameras, communication nodes, everything on there. And that all needs to start working on, generating maps, accurate maps to analyze, but then also very low-level maps to in real time, all on board the platform, and then also send it up to mine management. So currently we have a whole simulation environment, nice smooth video showing everything there. So we have a nice simulated environment that we're testing some of our algorithms on. We've also bought this lovely legged robot. So we're not focused on platform, we're focused on algorithms. So if we pick up our hardware, dump it on a nice spot or animal robot, then we'll have no money left, but it will still work. So we're focusing a lot on terrain-aware path planning. So we want to make sure that we do long-term automation. We don't want to autonomously explore an area once or twice or for a month. We want to do it for a couple of years. So we really need to know where this robot can and can't go, and the safety of the robot is paramount. Because if it gets stuck, we need to send people in to go and help it. So looking at that, and if you are dealing with very rugged terrain path planning when there is no path, there's just mud and rocks everywhere. Again, not focusing on this, but still trying to use old maps to see, where should we go, trying to define that task of what the robot actually needs to do, and then also generating multiple different maps, one that the robot can use to navigate and one that the mine manager can understand and see exactly what's happening in his mine. And some of the problems are they blast every single night, every single day. So it is continuously changing, and the robot needs to adapt to this. It also needs to get out of the way so that it doesn't blow up. And it also has to be around miners that might not like a robotic platform underground. Unfortunately, I can't go into too much more detail because it is covered by NDAs. But yeah, so if you are interested in that, you can chat to me. But we are looking at doing all of this inspection for these legged robotic platforms in these underground environments. So going forwards, open for collaboration. I think there is a talk in 2 days' time about collaboration. If you're interested in ESL or any other research we do, please reach out to me or to one of my colleagues. And that should bring me 33 minutes. Any questions? Yes.
Okay. I enjoyed your presentation. One question. Have you tried using one from your
We haven't done hydraulics. Pneumatics was great. It's easy. You don't care if it leaks. Things go wrong. It's just air. So we try to avoid hydraulics, but there have been quite a few publications on, I think, HiQ, the quadruped that uses hydraulics. So it is feasible, but we were more focused on cheap and easy, which, pneumatic cylinder with a pneumatic compressor, easy. And you don't have to worry about a return valve. You just vent it to the air, which is nice. It's also non-toxic. It's great. Any other questions?
Yes. That's really cool. Is there some sort of like Hansel and Gretel thing you could do by like dropping features as you go? The robot could really place markers or something.
Yes. So I had a meeting with a company called Match ID. They spray a speckled pattern on stuff and then see how that changes over time and estimate stress and strain in rocks. The problem is you blast and everything gets covered in dust. So what they're currently doing now is they actually spray paint markers and then they go drill at that marker. We're trying to avoid touching the surface. So we want to try and avoid putting markers down, because if you're continuously blasting, it's gone. Yeah.
Yes. My question is about the power requirements of that program. It looks to me like you're going to have a power-hungry robot. I don't know, how do you intend to solve the...
I tend to prove that this platform will work for an hour and then focus really hard on lowering the power. It's such a huge project. I'm throwing absolutely everything at it. I don't know how those conditions are going to affect different sensors. Getting sensors underground in an active mine is, to take those pictures was difficult enough. To take a sensor down that they don't know exactly what it does is going to be very, very challenging. So I am going to, when I get an opportunity to test, I'm going to have every single sensor I can think of recording information. I'm going to get it to work, and then I'm going to worry about making it last long. So yes, no, it is a big problem, but we are just throwing stuff at it to see what works, and then we'll optimize.
One question about the kind of terrain observation. So you put a husky with kind of 4 wheels. That's going to give you some idea about the terrain. You put an animal which is going to slip and slide. It's going to give you another idea about the terrain. How kind of are you picturing this kind of stable sense? Because the husky is like 50 kilos and is smaller. How does that extrapolate into humans and so on and so forth?
So I think the nice thing with husky is it's a low center of mass, and its wheels it's quite wide. So I think in terms of intrinsically stable platforms, I think it is a bit better than a legged robot. I really wanted to get a legged robot because I think they're really cool and I like legged robots. But the mining company was very much against that, and they said it's just going to fall over. Some concern, there's some validity in that. But yeah, I do think the husky has a better chance of surviving that environment. It's also got less moving parts. I think with that grinding paste from the material with metal in, I think that's going to really affect legged robots. And the guys on the ground that do the repair of these vehicles aren't going to be able to repair a animal, but it might be able to repair a 4-wheel robot. But yeah, we need to start analyzing terrain and figuring out, getting different ideas of what that terrain is doing.
Do you have like any enhancements to the husky that you have planned? Because we've taken a husky to a farm environment, and like after an hour of driving it in the farm, like on a hot day, everything overheated, and like while we were recording a bag, everything just shut down. So I mean, like in that environment, in that case,
there's water everywhere. Okay, so the approach of the company, they don't care about the platform. They're never going to use a husky underground. They care about the algorithms and the software. So they bought a platform that I can go and do feasibility tests and get something working to do a proof of concept. They will then go and take it on a docking robot, which can push a good few tons of material. They will go and mount that sensor pack on there and automate that. So the idea isn't to have a husky underground for long. The idea is to have a fun toy to play with and prove that these algorithms work, that the system works, it can map, it can identify. Then you just go and attach that to any platform in the world and it will be fine.
Yeah, but even when you're doing that initial inspection, like I said, for a farm environment, no enhancements or anything. So that's something maybe.
So we did get the IP protection upgrade on it and better batteries and all of that. But yeah, we shall see.
I think we can share some fail stories. That's all.
Yeah. Anything else?
Thank you, Curly. And then next we have Dr. Stacey Shield, who's from UCT. Also happens to be my colleague. Does know all of the speakers who have come today or curated this program so I can meet my friends. But Stacey is an incredible researcher. Yeah.
Or I'm good. Great, and I'm just going to quickly set up a timer on my phone. Just to keep time.
The sound is echoing here.
Yeah, there's a echoing.
Yeah, I did notice on that side in Callan's presentation as well.
Possible to just switch that screen off. Is it coming from that screen?
Yeah.
Fair enough. There we go.
Sound. Is it better? Yes. We'll switch it off.
On. Okay, yeah. Hi, everybody. Thanks, Paul, for the wonderful introduction. I think some useful context for that introduction that you might be missing is in my non-research part of my job, I teach the introductory feedback control systems course at UCT. So if anyone's familiar with Martin Braw or Edward Berger, you all know these guys. It's like those two guys and then me. That's the shoes I'm trying to fill right now. So what I'm getting at is, I mean, I just want people in my class to pass. It's a real struggle. But, so what I'm trying to get at is I've been working basically every waking hour for like the last 2 months. And then I heard about this conference that was seemingly being organized in about 3 days. Paul was just like, hey, do you want to come do this thing in Joburg? And I'm like, I would love to. I don't know how I'm going to make it happen, but here I am. I finished these slides last night at about 10, and then Steers here did me so dirty. They broke my heart. They cracked my psyche because I ordered cheese fries and they sent me like regular fries. I think someone had started grating cheese on it and then gotten tired of it after about 5 minutes. And it just completely snapped my brain, and it changed my plan a little bit because I thought I was going to come here and give quite a formal technical discussion of the things we've done. And I'm like, no, you know what? I'm the last thing standing between everybody and the welcoming event. Let's make it fun. Let's just talk, 10 years of leg robotics and related memories at the ARU. And it's a good time to actually have this recap now because, Amir is... He's gone off to UCL now. He's definitely not gone. I keep saying if I open my phone right now, he's definitely somewhere in my teams asking someone about a robot right now. But it is kind of in a way the end of an era at the ARU. So it's a nice time to reflect on the things that we've done and look at where we're going to be going forward. So for starters, though, before I get into all of this stuff, I'm going to just talk a bit about the ARU as well, because I am the only speaker from it at this event, apart from the students. So if you're not familiar with the ARU, we are UCT's robotics lab. This looks very nice, but I guarantee it doesn't look like this right now. I think there was like some clouds and a cold front rolling in as we were leaving. So definitely we got on the good flip side of the weather being on in this part of the country this week. This is us, Amir's still technically there because he's still very involved. But this is the rest of our 6 PIs that we have at the moment. And here is a good collection of our wonderful students. This was at Amir's farewell recently. And these really are the background driving all of these things. It's always like this year I've traveled a lot and presented work at a few different international conferences, and it's just every single time people are blown away at what South African master's students are able to do. Like the fact that the platforms I'm going to show you, each one tends to be built by mostly like one guy who's not even doing a PhD. People's brains just melt. So well done to all of these people. It's great. But yeah, so the African Robotics Unit, it's worth considering, you know, what do we mean by this idea of African robotics? How do we define that? And for us, it's kind of about two different things. It's on the one hand, it's asking how can we allow our location here in Southern Africa to have a unique impact on our research, but then also where are the places that we can have a meaningful impact on our location? What do the people of South Africa need from robotics? What can we contribute to this place with the work that we do? So the key, I'll show you our main research areas now and how they kind of fit into this definition. So in terms of being impacted by our location, I think the clearest and straightforward example of that is our work with MARIS, the Marine and Antarctic Research for Innovation and Sustainability Group. And we do a lot of Southern Ocean research with them. This is mostly Robin Verander's area. And it's a logical thing for us to do because we are the closest point to Antarctica. So obviously we're a great place to launch research vessels like the SA Agulhas 2 from. So we've made a little bit of a living as a research group being almost like tech support for those missions, sending unique instrumentation designed for this very specific and challenging environment on those voyages. In terms of having an impact on our environment and looking at unique problems in South Africa that robotics can solve, this is a lot of what Paul and his spatial intelligence lab within our group does, looking particularly at the application of computer vision, spatial planning, autonomous vehicles research to agriculture, because of course in our country, not only is agriculture a massive export for us and a very important part of our economy, but going forward, looking at things like climate change, food security is going to be something very important to consider. So if robots are part of the plan to create farms that are more efficient, more productive, and also less dependent on backbreaking human labor, then this is something that we want to be working in. And I'd say now our research in legged robotics and related fields kind of falls a little bit into both. Of course, on the one hand, it's something that's very influenced by the unique opportunity we have with our world-famous biodiversity in Southern Africa. Of course, every legged roboticist's favorite animal is the cheetah, but we have the unique advantage of sharing a homeland with the cheetah. So it might not seem like much, but it is something. So that's the way that influences us. But also, it's something where we get to have an impact, because one part of it is the way that research has often interacted with our wildlife falls under the banner of what we call helicopter research. It's guys from overseas just coming down to Southern Africa, publishing papers on these animals and making no meaningful contribution to local science, local infrastructure. And up until our research, the majority of the publications on the cheetah at an international level were all basically just done by guys at Royal Veterinary College in London. So at least since then, we've been a part of changing that. And now through our biomechanics work, there's a lot of publications on the cheetah that have been happening in recent years where there's at least a big part of the co-authors on those papers are South African researchers. So this research has also been very valuable in helping us be better custodians of this amazing wildlife that we're so blessed to have access to. But even with just, sorry, this slide is clearly a victim of my ambition last night. I was trying to like use AI for the first time to try to generate some icons, and it didn't really work out. So let's just pretend that there's icons. Even with what I just said, there's still kind of this question of why legged robotics. But maybe I should take a step back and even mention why I have a slide like this anyway, because no one else has come up here and felt like they needed to justify, like, why are we doing SLAM? But I think with legged robotics, at least based on my interactions with the public constantly, there's always someone going, oh, but wheels are so great, why legged robotics? And particularly in the context of somewhere like South Africa, it does feel like something that is worth asking, because let's be real, legged robotics is a bit of a science fiction technology. It's something that falls in a lot of ways more into that boundary pushing space program type of research than something that is incredibly, immediately, obviously useful on the day to day. So in a country that is as resource constrained as we are, where we have so few students, so little money compared to other places, it's like, why do we want to be in this space? I mean, it's telling that the top players in this particular niche field, it's your Boston Dynamics, it's your MITs, it's your ETH Zurichs, they tend to be institutions that are monuments to like what can be accomplished if you have all the money in the world and you run your lab like a gulag. And there's just something to me that's so appealing about this audacity that Emir came in with, to look at that and go, no, you know what, I think here we may have no money, but we have incredible talent, we have positivity, we have just sheer African grit, and maybe those things together, we can actually get a foot in this very intense, hectic, pay-to-play kind of door. So these are all the reasons that I think that legged robotics is something that's worth doing. I mean, on the one hand, it can help us, like, yes, as we just saw in Dr. Fisher's presentation, there are a lot of applications where legged robotics are genuinely, it's a useful technology. If we want to live that dream where, living in a future where tedious tasks, dangerous tasks, undignified labor is something that the robots do and humans are free to work on, works of intellect and creativity and imagination and all of those things, then we want robots to be working in all of the environments that humans currently are. And many of those are going to be a lot more accessible to robots that have a more human-like physiognomy than a wheeled robot can. So in particular niche cases, yes, legged robotics is useful. But let's be real, that's not why we do legged robotics. Or at least why I think for me, the biggest draw for legged robotics is more this sort of place over here, that it's a technology that can, in a lot of ways, teach us about ourselves. I think while we're here talking about the history of robotics, legged robotics draws all the way back to probably the earliest concept of a robot. If you look in most cultures, myths, and legends, there's always this idea of automata, of these human-like machines that are built. There's writings and examples of medieval attempts to create automata. Whether or not any evidence has actually been made has ever been found. It's very clear that for all of recorded human history, there is this interest in trying to create machines that can do the things that we can, that move the way that we do, that remind us of ourselves in some way. And I think probably a lot of that is because of this idea that you can't understand what you cannot create. So maybe by trying to create something like ourselves, we can learn a bit more about us as well. And this is with legged robotics. By necessity, you're learning a lot about legged locomotion, and that's very appealing to me. Outside of my job, the one thing that I feel like I have time to really be serious about is dancing. So just all around a person who's very fascinated by motion, movement, the control of those things. And I like to look at it from a lot of different perspectives. So being in a field where I get to kind of have like one foot in technology and one foot in biology is very appealing to me. And I think it's very appealing to a lot of our students as well. And on that note, I think another part of why it's important for us to do like robotics is that it is such an inspiring field. Maybe because it is something that is so relatable. It's something that I can see when you go to schools, when you have an open day, people really want to go and look at the robot dog or look at a humanoid. I think I was going to say that a legged robot is probably what most people picture when you say robot, but I am aware I'm talking to a South African audience. So for us, it's more that thing at the intersection with the lights and the guy like selling stuff. But anywhere else, if you say a robot, they're picturing like. So I don't think that that's something that should be taken lightly, something that's going to make people look at it and go, oh, that's cool. I want to know more about that. I want to study engineering. I want to go into science. We can't cede that advantage completely to the first world. We need to be doing the fun, exciting, cutting edge sci-fi stuff here in South Africa as well. Another reason to be doing that is because it can push technology further. If we ask the question, why can't robots move the way that we can? I don't know about you, when you watch the Olympics, what you're thinking, but a lot of the time I'm going like, wow, that's insane. Wonder what it would take to get a robot to do that. But a lot of the time you don't even need to be looking at something as crazy as the Olympics or Cirque du Soleil. Often it's just, if I'm running late for work and I have a bag and a bag and a bag and a bag, and I've gone down and I've gotten my cup of coffee, but now I'm going back to my office, and you have to kind of like suddenly navigate the fire door, and you're doing like one of these, and then you get to your office door and your keys are in your bag, so you sort of fish it up with your pinky, and then you do that thing where you flick it up to kind of catch it. You just do all of that, and when you start thinking about it as a contact-rich manipulation task, like how would you even? So there's so much stuff that we do that we take for granted and we see animals do, which we are still so phenomenal. Clearly my contact-rich manipulation is, I did just say, like, sleep has been scarce for me. So when we start asking why robots can't do these things, it reveals so many opportunities to be pushing the boundaries of the technology that's there already. And obviously, when you're pushing the boundaries of that technology, you're creating things that can lift up various other sectors as well. So for more detail on that, we consider legged locomotion in a very general, zoomed out way as a feedback control problem. As Cullen showed, it's really more a bunch of interlinked feedback control problems if you're even doing something as simple as traditional feedback to control it. But really it is just on a certain level, you have a goal you're trying to achieve, you have a system that you're affecting with actuators, you're using your sensors to see if your system is doing the thing you want it to be doing. And there's a bunch of places in this loop where we can ask ourselves, is this the place where robots are falling short? Things like, is it about the mechanical design of these robots? Is it that they need stronger actuators? And when you actually look at most of these things, robots should be better than we are because they have the ability to be stronger than we are. They have the ability to be designed mechanically a lot more optimally than we are because they just have to move. They don't need to do all the things we need to do, like eat and sleep and all the tasks of being a living being. Maybe there's an argument that robots are quite behind us from a sensor perspective, but I think really it's this control place where you really start to see the differences in why humans and animals can do the things we can and robots can't yet. So legged robotics is something that's definitely going to push the control of complicated mechanical systems further, and that can't be a bad thing to do that. And that's especially true looking at the particular area of legged robotics that the ARU has decided to focus on. Most of our peers in the field have aimed more at trying to develop sort of commercially viable systems where they are looking a lot more at just stable locomotion, robust control. But we've decided to push the final frontier and look at rapid high-speed maneuverability. So looking at animals like, of course, the cheetah and trying to understand how is it that these animals not just move as fast as they do, but transition the way that they do at those speeds, how they turn, how they stop, how they accelerate. I mean, a cheetah can reach its top speed in just 3 strides. It can accelerate basically as fast as a superbike. It's insane. So what are the unique features of these animals that we can try to replicate? So maybe if everyone else is just trying to build sort of a utilitarian kind of transit van of a legged robot, we're out here trying to build a Ferrari. So we have got quite a unique niche from that perspective. So this phrase here, how can we clock the cheetah? That's something that Amir said to me once. I assume he wasn't talking about punching a cheetah in the head. I don't think that would go very well for anyone, but especially Amir, because I think a cheetah has, a cheetah's in a higher weight class than Amir. But I think he mentioned more in the video game sense of like, how do we get kind of 100% completion of doing what the cheetah can do on the roadmap? And in trying to answer that question, it's taken us in quite a diverse array of directions where it's not just the business of building robots, it's controlling them, it's looking at biomechanics, it's understanding more about legged locomotion. And a lot of that has had really amazing offshoots in the design of field biomechanics technology as well. But don't worry, we're going to be getting into all of that. So this is a rough timeline of the ARU's publications in legged robotics and related fields. This isn't obviously all of them. It's just some of the key points. It took me a while to figure out exactly how I was going to present this information, whether I was going to go kind of line by line, but really it's such an interconnected journey that the only way to really make it make sense is to go pretty much chronologically, year by year, what are the things that have happened in the ARU. So let's begin with back in 2013, 2014, the robot Dima. Where it all began. So this was Amir's PhD project. It was, and yes, I know this is about leg robotics, and I can see Dima has a tail, but I mean, and wheels. But Dima is, at least conceptually, very much the start of where our leg robotics would take us. This is the start of our interest in this cheetah and the start of our interest specifically in rapid maneuverability. What you can also see in the picture there, this is like back in the original version of our lab. It wasn't called the ARU back then. We were just this loose collection of master students and PhD students working on vaguely mechatronics related topics. And they just put us in what is literally now a storeroom. It's like this horrible little room at the back of UCT's control lab where there's like no natural lights after 2 p.m. because it like faces into an internal courtyard and you couldn't like push out your chair without like hitting the person behind you. So this is sort of our humble beginning. And then, okay, these are just some of the publications on Dima. Then from there, another thing that we branched into immediately from Dima was actually doing real hardcore research in this biomechanics space. Because as exciting as it was to see with Dima that cheetah-inspired movements of the tail that we'd seen just by observing the cheetah, when it decelerates, when it turns, there's repetitive motions that we see that seem to correlate with the idea that the tail is being used to balance itself. As much as it is exciting when you apply those movements on a mobile robot and get improved control because of them, the exact way that you hypothesize the cheetah is doing, that doesn't amount to proof that that is actually what the cheetah is doing. It's just proving that required data that at the time just simply wasn't available. You need to actually have real 3D full body motion capture of the cheetah to be able to say when its body moves like this, its tail moves like that, and show that there's a feedback relationship. So after Dima, that's something that we wanted to look into doing, is actually showing, in this cyclical way where the animal inspires the robotics and then the robotics methods inspire the way we approach the biology, could we then look back at the cheetah and see if we could find out more about the way that it moves? And this started us off with looking at these taxidermy cheetah tails. What had happened was, after DEMA, we realized that when we went and did necropsies of cheetahs, which, as Karen said, we didn't kill any of them. What actually happens is that every time a cheetah dies in a national park, they have to do a necropsy of the body because it's an endangered animal. We need to know if there's a sickness or something that's killing them. So there are people you can phone up and just say, hey, if any dead cheetahs come across your path, can you just invite us over? And when we did that, we found that the cheetah tail in relation to its body was a lot lighter than we expected it to be, especially compared to DEMA, where I think the tail was about 10% of the body weight. I think the cheetahs was down to around about 2%. So we went, well, we thought this thing had an inertial effect, but this counteracts that viewpoint. But then you look at the tail and you see how fluffy it is, and especially towards the tip, it seems to be consistent with the idea that maybe that fur is also having an aerodynamic effect that could increase the amount of torque it's exerting on the body without increasing its weight. And we wanted to find that out. So we got these tails. Maybe the first batch we just put in the wind tunnel straight away without doing anything to them and just tested them until they rotted. But we got a few more, and I'm like, why you guys are doing that when you can just put them in some borax? And it turns out that every skill you think is going to be useless in life actually becomes useful sometimes. And I did a week-long taxidermy course in high school, so I mounted these tails on a threaded bar. It was a fun time in the lab. No one would allow me to do it inside, so I literally had to climb out the window and do it on the flat roof outside our new lab premises. I did unfortunately lose one to the southeaster. I put them out there to dry, and our colleague Arnold, he had some weights that he was using for some drone tests that he was doing. I'm like, well, okay, wind's picking up. I'm just going to weigh these down. And there's a 10 kg weight on each tail. Came back the next morning. 2 of the 4 tails are there. I'm in high heels. I'm running around on the roof looking for this thing. People down the bottom are like, what? And I see in the distance in the tree, there's one of the tails. So I ran there and grabbed it. So I'm coming back and I see some of the cleaning stuff. I'm like, have you seen one of these? And they hadn't, so I was never seen again, alas. But we had these 3 tails, and with them we showed especially in the roll direction, the tail does have a significant effect, particularly at speeds matching how the cheetah would run in the wild. So the year after that is when we started getting into trajectory optimization for the first time. With this paper looking at optimal sprinting in quadrupeds. So I'm happy that Callan didn't get more into this because I was like, oh no, are both of us going to give a primer on trajectory optimization? But he didn't. So I'm just going to give you a brief description of what this is if you've never heard those 2 words put together before. So trajectory optimization is kind of a simulation method, but what's unique about it is most of the time when we're doing simulation, you either need to know the force profile or you need to know the sequence of states. It's either you're asking what happens to the system when these forces act on it, or you're asking what forces do I need to produce this sequence of movement. With trajectory optimization, you don't know either of those things. Most of the time you have an initial state and you have a final state at best, and you're asking, if I have this mathematical model representing the dynamics of the system, what is a physically feasible way to get from state A to state B? And it might be that there are many possible feasible ways to do that. To make a stupid example, it's like I could walk over there, but I could also skip over there. I could run over there. I could do, well, maybe I couldn't, but someone could do a sequence of backflips over there. All of those are ways to get from A to B, but some of them are going to fulfill the the cost function better than others. So that's where the optimization part comes in. So if you were, say, minimizing actuator effort, maybe walking is going to be better than doing the backflip. So that's the trajectory that you would hope would emerge from your simulation. So what's quite nice about this is it's obviously a great way to study movements where very little is known about them. And that is very much the case with these rapid maneuvers. Compared to movements like even constant speed locomotion, where we have words to describe it. You know, we know what a run looks like, we know what a trot looks like, or a gallop. If you look at even the same animal stopping multiple times, its behavior can be very, very different every single time. And that could be because of so many things. It could be terrain differences, the morphology of the animal, the moment within the stride that the stimulus requiring it to stop was registered. So maybe you see the obstacle and all your feet are in the air. Maybe you see the obstacle and some of your feet are on the ground. The point is that unless you have a reliable way to start the problem from exactly the same conditions every time and control for all of these variables, it's very difficult to isolate what is creating these different behaviors in these maneuvers. And that's completely ignoring how difficult and how dangerous it is to get these maneuvers executed, maybe in a living creature or robotic platform in the first place. I mean, most of the time, a cheetah is not going to be stopping from full speed unless there's a real problem, and it just simply wouldn't be ethical to do that kind of testing. So as you'll see, trajectory optimization becomes a very big part of our methodology in the lab. We use it in various different ways. So I thought it was worth just elaborating a little bit on what that's all about. So this is where we're at. We started using this in 2016. And the year after, I actually got my first legged robotics publication in trajectory optimization, doing something similar to this, looking at optimal bipedal stopping. So the initial ways that we were using it were very much looking at the optimal way to do a movement. Pretty much exactly what you'd think trajectory optimization would be used for, the more common way that you see it being used. But here with this publication that Callan also talked about was where we started flipping us on its head a little bit and also started using it in the design. Because of course, once you're setting up movement as this giant nonlinear programming problem where you're choosing the design variables, maybe those variables are the states and controls that your system is using to move, but maybe some of those design variables can be the actual morphology of the thing. And it's also another way that we can compare as well, sort of broad classes of methodologies, of morphologies. So you have a rigid spine robot, a robot with a revolute spine, and a robot with a prismatic spine. And you want to know generally across a bunch of these trajectories, which of these is tending to produce the faster robot. And we found that a prismatic spine tended to do that. So put a pin in that for later. So in 2017, another important thing that started happening besides us using trajectory optimization in the design of robots was that we really, for the first time, started actually working with tracking the motion of real live cheetahs. This was just a little bit on the cusp of when GPUs were starting to allow neural networks to become a real feasible thing that you could use, for various purposes, but particularly for motion capture. So we were still very much in the sensors on an animal phase of things. At this time, the only comparable study had literally been with one sensor on a cheetah's collar, and it had just been looking at kind of the top speeds that they reach and the accelerations that they use during hunting. But it's still a cheetah equals one moving point. There was no one had even attempted to do any kind of full body or even partial body reconstruction of the cheetah movement. So this was to have this harness with this camera, is because of course we have to do everything in the lowest cost way we can. We just had an Android camera on the cheetah. We had some stickers on the tail, and there's this awesome video where it's literally like riding on the back of a cheetah and watching its tail swing. So We get to 2018, and this is the first time we introduce a legged robot. Baleka, Callan told you a bit more about it, so I'm not going to spend too much time there. But besides being, to our knowledge, the first African legged robotic platform that had been built, it's also the first biped that had been built specifically with maneuverability in mind, and it had one of the most powerful vertical jumps of any bipedal robot in the world at that point. So 2019 brings in a really game-changing breakthrough for us, and this is when we actually start using machine learning as a way to do motion capture with the cheetahs. As much as we got in, at least of the spine and tail, the ability to do 3D reconstruction with the sensors that we put on the animal, a cheetah is, of course, just a cat. And that means that sometimes we put a sticker on its tail and it decides its legs don't work anymore. So with an animal that's as fussy as that, and especially if we want to move from working with the more relaxed, tame, captive bred cheetahs to actually looking at these animals in the wild, we needed a much less invasive way of doing this. And markerless motion capture was just that. So there's a package called Deep Lab Cut that has become one of the industry standards for field biologists to use for this. And when they were first making their algorithm public, we provided a really incredible, truly wild example of what this could achieve. We had all of this footage of cheetahs and we said, hey, can we collaborate here? And this ultimately became a cover story for Nature Protocols, was Deep Lab Cut with our awesome cheetah data. Happened around about this time, 2019, 2020 was, I published the majority of the research for my PhD. So I took the trajectory optimization that we've been doing and started doing kind of a new approach to it compared to what other people were doing in the field. So rather than just using trajectory optimization to ask one time, what is the optimal way to do this motion, maybe with the intention of just running it on the robot right there, I started thinking about it as a method of generating synthetic data. So the thing with trajectory optimization is that in an ideal world, what the solution that you get out of that nonlinear program is the best one. But in reality, when you have a problem with a couple of 100,000 variables and a bunch of nonlinear constraints, it's extremely difficult to solve, and it's also completely impossible to prove mathematically that the solution you get is truly the optimal one. So the way that we'd actually been approaching the business of generating optimal trajectories is by generating as many as we could from many possible starting points in the solution space. And depending on where you initiate that optimization from, you're going to get different results every single time. So what I started doing is going, okay, maybe this is something that we can use to our advantage, because ultimately for our purpose, we were less interested in that one best trajectory that we could execute on a robot and more interested in is that trajectory good. So if you do generate, say, 1,000 different trajectories and you can arrange them in order from the lowest or the worst satisfaction of the cost function to the best satisfaction, and you start looking at these trajectories one after the other, if you assume that your mathematical dynamic model is in any way reflective of reality, maybe it could be that the features that you start to see emerge as the runs get more successful are also features that would make a real-life robot more successful when it tries to do that maneuver. And I think probably also the people into RL in the room, like maybe I really hope that you're kind of lighting up, because I'm sure that you can see the application for collaboration over here. I'm definitely really excited to potentially take this more white box approach to learning how a robot can move and implementing it with the more black box approaches that are gaining prominence in robotics as well, because I think probably some combination of this with the more reinforcement learning type of approach would actually be the happy medium. So if anyone wants to talk to me about collaboration, really in any space, but particularly that, do let me know. Shame your battery is dying. This is, hopefully we make it, because the button is not buttoning now. Okay. This is just an example of a figure where this is from the paper where I first kind of posited that idea. And you can see this leg swing pattern starting to emerge as the trajectories get better and better. So this, sorry, I'll come back. Following this approach, once we realized that this is maybe a useful way to use trajectory optimization, it created an interest in improving the way that trajectory optimization itself is done, because obviously if you want to generate 1,000 different trajectories, you need your optimization problems to run really efficiently. So a lot of my research was around looking at all of these different factors that you have control over at the problem formulation level. Not looking at the solver level. I don't have a PhD in applied maths, nor do I want one. I have absolutely no idea how IPOpt or any other nonlinear solving algorithm works. It's just this magical black box that the problem formulation goes into and then results come out. But there is a lot of room to innovate at that level and go, okay, what method of numerical integration is going to come out with the most accuracy and the most computational efficiency? What are the different ways that we can, model our system using different coordinates? What are the different ways that we can navigate the biggest challenge of doing trajectory optimization for legged robotics, which is the intermittent state of contact with the ground, which introduces non-smooth dynamics into the problem. So all of these sorts of questions were the things that I tended to be asking in my PhD. So pretty much this whole branch is just innovations on how to make trajectory optimization faster, more reliable, and produce more diverse results that we started doing in order to feed this idea of using it in this sort of synthetic data generation way to study leg maneuverability. So following that in 2021, we get another major breakthrough in our motion capture branch that is very much the culmination of the things that had come before that, where now that we could do markerless motion capture, we could apply that to all of this cheetah footage that we captured at Cheetah Outreach in Cape Town, and particularly Anfindek Cheetah Center, more kind of on this side of the world. And we produced what is the first data set of 3D reconstructed cheetah locomotion called a CinoSet. This is just the experimental setup that we use for that. So we use 6 GoPro cameras surrounding the track where they would run for exercise at Anfindek. And we tracked 23 points on the animal's body to create this 3D skeletal model. And to complete this and get that reconstruction, we invented a method called FTE, full trajectory estimation, which kind of leveraged our knowledge of trajectory optimization to create what is effectively a very fancy common filter to help us identify where these should be in situations where they were maybe occluded or Deep Lab Cut just struggled to find them. Because of course, when you're filming an animal and sometimes it's very far in the distance, it's in different conditions, and ultimately you're filming them in an environment where the animal is, colored to camouflage into the background, sometimes you're not always going to be able to spot every single part of it. So that's how CinoSet was created. So another sort of maybe slightly less publicized thing that we did at this same time as the CinoSet was, this was also the first time we started applying these techniques that we'd been developing to human biomechanics. In particular, we started working with the Sports Science Institute at UCT and seeing if it could be applied to evaluate the safety of tackles in rugby union. And that started a whole journey of working with sports science that will come back in some other things that we've been doing. Following that, 2022 was very much our year of low-cost biomechanics. So we had a paper about improving motion capture using these low-cost cameras, because in this world, in this space, GoPros do count as low-cost cameras. How can we make it more effective when that's what we're using? And also developing this low-cost force plate, which we now have, I think the patent has been granted, yeah, on this idea of using a force plate that applies machine learning to make up for using fewer sensors. And through both of these things together, we've developed sensors with wide applicability that can make field biomechanics a lot more accessible to under-resourced labs like ours, but also potentially in clinical settings like the way that sports science is using it there, instrumental in some of this development, and potentially applying it throughout the country to help with rehabilitation. So now, 10 years after DEMA, we finally get to Kemba. I call them the ARU's heir apparent, and that's mostly just a pun on the fact that this is a partially pneumatically driven robot. But Kemba really is the heir of everything, the inheritor of everything that we've learned in all of this time. Not only is Kemba a cheetah-inspired robot that uses pneumatics because of the things that Callan talked about, where we understood that you just need that explosive actuation. I mean, no one in leg robotics tends to use pneumatics because of the fact that they are this bang control type of actuator. But when you actually look at the way that the cheetah itself moves and the research that Callan did, we saw, well, hey, if you have a process that is inherently kind of bang in nature, maybe that's fine. So not only is Kemba sort of mechanically and conceptually very much sort of this combination, it's also trajectory optimization was heavily used in the way this robot was designed. So it really did take all of these things that we've been learning up until that point to create this robot. Following Kemba with our work this year, we get Aerodema. Yes, I know it's 2024, everything is reboots and sequels. But what makes this version of DEMA exciting is this DEMA draws on this research we did all the way back there on the aerodynamics of the cheetah tail and asks, if we equip this robot with an aerodynamic tail rather than a heavy tail and make that the primary mechanism of affecting torque on the body, can we still achieve similar improvements in maneuverability performance to the original DEMA? And it turns out, yes, we could. Another very exciting thing that we published this year is Wild Pose, which is also sort of a culmination of a lot of our field biomechanics work up to this point. So Wild Pose is a multi-sensor camera system that's also equipped with LiDAR that can do 3D reconstruction of animals in the wild up to 200 meters away. And this is a comparison to competing systems, and you can see we are just dramatically far ahead of the competition there. Here are some examples of these incredible morphological point clouds that we're able to generate. Like this is 200 meters away from a giraffe, and we can get this incredible reconstruction of the animal. So really excited to see that applied to cheetahs at some point in the future. But of course, at this point, it's useful so far beyond just our own individual projects. And another thing in this general area of research that we developed this year is, for the first time, we started using our knowledge of trajectory optimization in combination with this high fidelity 3D motion capture that we have to start doing 3D force estimation from footage of cheetahs. So asking, if we can get this rendering of how the animal is moving, can we identify the forces that probably produced it? And this is a comparison between our estimated forces from this method and actual literal ground truth, ground reaction forces from running a cheetah across a fourth blade. And you can see it's obviously not perfect, but the orders of magnitude are kind of in the right place, and it's definitely going to help us get to that point that we wanted to back when we first started looking at DEMA, of being able to ask, this thing that we think is happening, is that actually what's happening in the animal? If we look at this interaction between these forces and the animal's motion, do we really see this feedback relationship with the cheetah's tail? Do these things work the way that we think they are? It took a while, but we finally got there to the point that even if we haven't necessarily gotten the data yet, we have the means to do it now. So this is where we've been. This is where we are now. And I'm just going to end off by asking kind of where's the ARU now going in each of these directions. So this is our forthcoming attractions. On the Kemba front, we're about to release the second version of Kemba. It's built. We just need to get that paper in. But I'm not going to go on too much about that. This is where that spine research that we started gets actually applied in a real robot. And my student, Shalom, is going to be talking about it at the paper session tomorrow. On the locomotion research front, we have a really interesting ongoing project that kind of happened quite serendipitously starting last year, where we've been filming cheetahs in the back, being driven around farms in the back of a bucky, and seeing, when this car goes over a bump and it uses its tail, if we can identify that feedback relationship in a much simpler context. My other student, Cam, is going to be talking a bit more about that tomorrow morning. And this work is part of a more in-depth ongoing project that she's also part of, where we're taking this trajectory optimization and now we're flipping it around. So we heard about inverse reinforcement learning earlier today. This is very much the same idea, where now we're starting from the point of view of having the locomotion in front of us, and we're asking, what is the cost function that produced this locomotion? Another thing that we're doing on the locomotion front that's also kind of a inverse trajectory optimization type of idea is I'm doing some research with Janneke Schwaner, a postdoc at UC Irvine, on kangaroo rats and trying to prove that they use their tails for aerial writing and show evidence of feedback control there. So hopefully when undergrads stop being so much, that will be another paper that we get in this year. With motion capture, where that's going is this year we are starting work on a senior set 2. So taking all of these things that we've learned, all these new things that we've developed, like wild pose and remote force estimation, and creating a bigger, higher fidelity, better data set of locomotion. And the other culmination of all this work that we've been doing is this feed called Wildlife. This is a project that we're working on with Sandparks, where the idea is to combine the remote motion capture stuff that we've been doing with remote vital sign detection and create an all-in-one system that can do remote health monitoring for animals in national parks. So the idea is to have the system at a watering hole or something like that and have a model of a healthy animal. And if you see, say, like a zebra that's walking around maybe a little bit strangely, the model compares that observation to the healthy zebra and says, hey, no, something's not lucky here. It can just call a park ranger in. So it will be just, as I say, a way to be better custodians of our wildlife and look after them using this technology that we've developed in this robotics context. And as for the final new thing that we're doing, we recently got this robotic platform, a little Unitary Go 1. As Cullen said, in the space that we've been here, or in the time that we've been here, Lake Robotics has very much moved on from just being about building your own platform to a place where there are really great existing platforms that you can buy and modify and test your own control on. So that's exactly what we're aiming to do with this guy. We've named him after Martin, after the late Martin Braw. And what we're hoping to use him for, at least in our leg robotics adventures, is testing out many of these developed through trajectory optimization and seeing these features that emerge when you use trajectory optimization for your data. Is that something that can cleanly be applied to a real life robotic platform to make it more maneuverable? So thanks everybody. It's been a wild 10 years, and I'm looking forward to another 10 and another few more after that, seeing where this goes. And yeah, hopefully the one thing that we can be doing more of in that time is more collaboration with our fellow local institutions. So I really hope that we'll have some good conversations this conference and start doing more of that.
Do you have any questions?
So maybe one question regarding the whole discovery of pointing the legs angle towards each other. So you mentioned how that morphology is, you got discovered that is the best in terms of like creating the highest like max speed in the shortest amount of time from starting. What is like? Is there like a trade-off of that? Because like for example, when you see the boson dynamics one and the unitary one, they are all pointed in the same direction.
Yeah.
Is there like a trade-off between putting them in like angling in the same direction? That kind of maybe is the reason why unitary and boson dynamic don't do that. And
yeah, so I can only speak to why they didn't do that, and maybe I can work more directly on the paper, so maybe you can also chip in with the reasons. But my recollection from that paper is the X-frame one that we ended up selecting was, in a sense, the trade-off was more between acceleration and deceleration, because we weren't particularly looking at top speed. We were actually looking at maximum acceleration in both of those directions. So how can we make a robot that slows down as quickly as possible? How can we make a robot that accelerates as quickly as possible? And I think the reason that the X-frame ended up being the most optimal is because having rear-facing hind legs makes your hind legs a lot more able to push off the ground and accelerate you, whereas having front-facing forelegs helps you control your body as you slow down. So the forward-facing front legs were better for deceleration. The rear-facing legs were better for acceleration. So the two of them together kind of gave a bit of a best of both worlds scenario.
that's it. That makes sense.
The end idea is to actually have a leg that can change its orientation in midair. So you go from facing all back to facing all front to X to whatever you want.
Yeah, I think I'm not sure. I think the most recent version of Animal has that actually, where it just has completely like universal joints in its legs.
I see. And so like, would the hypothesis, or will this hypothesis be correct, which is, so when starting, you want to get like the most acceleration, you want the legs to be pointing in the direction of movement, and then like as you are kind of trying to kind of like maintain that speed, or as you have to do your deceleration, you switch the leg that is behind to be pointing, or you switch the leg that is in front to be pointing in the X direction, so that it can smoothly kind of like decelerate quickly. And once you do that, if you want to reverse direction, then you also reverse the other leg. Does that hypothesis make sense? Okay.
Thanks for that talk. It was very educational. I was curious about, you mentioned a couple of times you talked about kind of designing on a dime and so I've been doing some work in Botswana, so I wondered about translating some of your development to my colleagues there. And can you talk a little bit about cost? I know you've been doing a lot of experiments within the lab, but kind of if they want to kind of go through a little bit of that process of learning mechanical design, learning that process, are those systems transferable? And in terms of like development, from scratch, almost like how your lab grew from out of mechanical design to where it's now.
I definitely think, yeah. So I think all of our designs are to some extent in the public domain because we wanted it to be a bit like the MIT Cheetah, where, for instance, they developed their own in-house motor design and firmware that is optimal for that kind of legged robotics. And now so many of the motors that are used in this field are just either commercially made versions of those motors or whatever lab you're in, if you have the capability, you can just build their same things. So I'm sure that if you didn't have the personnel to design something like a Baleka or a Kemba from scratch, we could give you the thesis, we could give you the plans. In terms of actual costs and numbers, I was mostly a PhD student in a corner somewhere doing trajectory optimization when a lot of the components were being bought, but it's definitely it's still an expensive field. It's always going to be an expensive field no matter which way you cut it, but we do it in as cost effective a way as we possibly can. It's just a limiting factor at the moment is always going to be like the motors that we buy. What's the most recent ones? Like
Steady motors and the other two motors, but from China.
Yeah, so we've been getting these AliExpress motors, and even from there, it's still sort of $6-7 grand a motor. So big robot like that, even a half quadruped, is still going to be sort of a 20,000 rand project. But I think as there gets to be demand for it on this side of the world, we've already started talking in our lab about the advantages of potentially having at least like the South African capacity to produce the motors on our side. Because another big problem that we've been having is when you order those motors from overseas, especially from China, a lot of the time the data sheet doesn't match the motor itself. When you go in and you do your system identification, you realize, oh, that's not the torque constant of this thing. We actually have no idea what it is. So even just from the perspective of being able to do our work better, it would be better for us to develop our own motors eventually, and that would also maybe bring the cost down. So hopefully that's a future thing we could look at.
Yeah, I think I would agree with that because I find that that's one of the limiting factors. Actuator.
Oh yeah, 100%.
That cost down will change the face of a lot of the development in Africa.
Yes, definitely. And I think that's also a huge opportunity that comes from gatherings like this, because it's like, if it's just us in our lab and Karen in his lab working over there and you in Botswana and someone else over there, and we're all doing these things individually, the economies of scale is just that we're all going to end up buying expensive motors from China. But if we can get all of us together, maybe there's a future for that.
Thank you once again, Stacey. I guess thank you for really interesting legged robotics / mining.
Legged robotics, tailed robots, mining robots.
Animal session. But I mean, it's all for us. Robotics. I think now we will end our technical session and we'll start.